Good afternoon, everyone, and welcome to the 2020 Department of Mining, Metallurgical, and Materials Engineering Professorial Chair Award Colloquium. Okay, this is Neri Cuenga, and I will be your host today. And I hope everyone is doing well. Before we proceed, let me just read you a few house rules and reminders. Nag-move ba? Hindi ata naka-play. Ayan. Okay, for our house rules, so to all our panelists, please mute your microphones unless directly addressed to avoid distractions. We will have a dedicated time after each presentation for your questions. And you may utilize the Q&A feature for our attendees for your questions, and these will be entertained during the dedicated Q&A portion after each presentation. For those who would like to request a certificate of attendance, we may issue upon request, and the mechanism will be announced at the end of the program. So please stay until the end so you will be able to request your certificate of attendance. Okay, to officially start the program, may I call on, let us hear from the department chair of M. She has a PhD in material science from Washington State University and a postdoctorate at the University of Colorado. Her current research interest involves photoactive materials, energy harvesters, optical spectroscopy, and surface science and engineering. To give us the welcome remarks, here is Dr. Candy Mercado.
Thank you very much, Neri. A pleasant afternoon to our donors and attendees from academe and industry. I would like to welcome you all to the 2020 Professorial Chair Awards
Doc
Colloquium.
Candy, I think nakamute pa po kayo. I'm sorry.
Is this okay?
Yes, Doc.
We can't hear you pa rin po.
Clear.
Neri, they can hear me.
Ayan, okay na po. Sorry. Okay, go on.
I would like to welcome you all to the 2020 Professorial Chair Awards Colloquium of the Department of Mining, Metallurgical, and Materials Engineering. Today, you will hear about the various researches of our faculty, starting from a session on materials for energy, environmental, and biomedical applications, followed by a session on clean and sustainable developments in extractive metallurgy. And then lastly, a session on enabling technologies, which focuses on electro and physical metallurgy. I would like to take this opportunity to say we are very, very grateful and thankful for our donors for their support in our professional growth, especially for our faculty. For our listeners and our attendees in this colloquium, I would like to encourage everyone to ask questions and make this session very lively. I hope you all gain insights from these talks. Thank you very much for attending.
Thank you very much, Doc Candy, for your message. We can now move on to our first session. So we have session 1, the materials for energy, environmental, and biomedical applications, to be moderated by Assistant Professor Joy Marisol Maniaul. Ma'am Joy?
Thank you, Neri. So good afternoon to everyone attending this event. So I would be presenting for our first session on the materials for energy, environmental, and biomedical applications. So our first presentation for today is entitled Pitting Corrosion of Stainment Pins and Stimulated Body Fluid. And our presenter for today is one of the pillars of the department, Professor Emeritus Manolo G. Mena. So he was recently awarded Professor Emeritus and Gawad Chancellor for Natatanging Guro in 2020. Dr. Mena has served both the academe for over 40 years and he has over 20 years of experience in semiconductor packaging, failure analysis, and reliability engineering. Aside from this, he has over 60 technical publications and 40 patents. He is also currently serving as the director of the UP COE National Graduate School of Engineering. Ladies and gentlemen, it's my pleasure to present our speaker for today for the Don Benito Yao Metallurgical Engineering Centennial Professorial Chair Award.
Good afternoon. So today we're going to talk about pitting corrosion of Steinman stainless pins in simulated body fluids. This work is done in cooperation with our graduate student Stephanie Santos Limlioco as her master's thesis. The Steinman pins are used for initial fixation of fractured bones. They are stainless steel pins equipped with trocar bones for easy penetration into a drilled bone. So these are x-rays of the Steinman pins being used to hold fractured bone in place. This is how it can look like after the pins being immobilized. This particular application is on fingers, which you may have seen in the Marvel movie of Doctor Strange. So, by requirement, Steinman pins should be made out of 316L stainless steel. The difference between 316L and the standard 316 steel is that the carbon content is lower from 0.08 maximum in normal or standard 316. It is reduced to 0.05 in 316L or low carbon steel. Such is done in order to reduce the formation of chromium carbides, and because these chromium carbides reduce the amount of available chromium for the passivation on the surface of the stainless steel. 316L is characterized by good biocompatibility, high mechanical strength, relatively good corrosion resistance. Most of all, it's cheaper than titanium, aluminum, vanadium alloys. In 2015, the Philippine Orthopedic Center used 1,932 Steinman pins in on their patients, and worldwide use is expected to reach 2 million by 2022. Now, even though Steinman pins are biocompatible and have good corrosion resistance, human body fluid, particularly the human plasma, is quite corrosive, and it can result into a pitting corrosion on the surface of the pins, and as a consequence, chromium, nickel, and iron gets released into the body tissues, and this can result into sepsis or poisoning of the body tissue. That is why the recommended medical practice is to use the Steinman pin for not more than 2 weeks. Unfortunately, in a lot of the local application, because of the cost involved in buying the more expensive titanium, aluminum, vanadium alloys, the Steinman pins are left in place for much longer than that. So this study will investigate the tendency towards pitting corrosion of locally available pins. These are the ones that you can buy around orthopedic hospitals. We will use the 3-electrode setup where the Steinmann pin is the working electrode. Platinum is used as the counter electrode against silver chloride as the reference electrode. The setup is immersed in a water bath and the temperature controlled 37 plus or minus 0.5 degrees centigrade. Electrochemical studies are used using an autolab potentiodyne. So the characterization techniques for the working electrode will include X-ray fluorescence spectroscopy, optical emission spectroscopy, scanning electron microscopy for surface analysis, as well as energy dispersive X-ray for compositional analysis. Optical microscopy is also used for surface analysis. Now, cyclic voltammetry will be the electrochemical method used to determine the tendency of the steel towards pitting. In this cyclic voltammetry runs, we will start at 0.25 volts against the open cell potential or the E corrosion. Increase the potential until it reaches plus 0.844 volts against the silver chloride reference electrode, and then bring back the potential down to minus 0.25 volts against the open cell potential. In general, if we look at the current as the controlling parameter, the reverse scan is done when an equivalent current to 1 ampere per centimeter square is reached. Now, a hysteresis is going to be observed when you perform cyclic voltammetry, and the size of the hysteresis loop is an indication of the tendency of the material to pit. If the hysteresis loop area is large, then there is a high tendency towards corrosion. If the hysteresis loop is small, then the tendency is towards less pitting corrosion. The potential at which the current starts to rise, or the what we call the E pit against the E pro, which is the temperature at which the stainless steel is protected, or the passivation temperature, is also a measure of the tendency to corrode. The larger the difference between E-pit and E-pro, then the higher is the corrosion pitting tendency. Of course, it should be intuitively obvious that if the E-pro is higher than E-pit, then your hysteresis loop is going to be much smaller, and therefore the tendency towards corrosion is reduced. For this particular work, simulated body fluid as formulated by Kokubo is used. We cannot use real body fluid because of the tendency towards clotting. And as we can see here, the Kokubo SBF, or simulated body fluid, has very similar composition to blood plasma. It has a higher chloride content, so any tendency towards pitting corrosion will be easily seen using this simulated body fluid. So we were able to get 3 samples, sample A, B, and C from vendors around the Philippine Orthopedic Center, and we use both XRF and Spark OES in order to do to determine its composition. X-ray fluorescence, as shown here, is only able to identify the major components of the steel, and is basically limited to the surface analysis. So by XRF, we can say that samples A, B, and C are basically similar or the same. But if we do spark optical emission spectroscopy, then it becomes very clear that sample B and C, as shown here in the result, conforms to AISI 316L specifications, but sample A is actually a 304 stainless steel material. And the parody of the situation is that the vendor for sample A is actually even showing a certificate of conformance to convince customers that the material they have is 316 stainless steel. So these are samples of the cyclic voltammetry for the materials. This will be the pitting potential, and this will be the protection potential. As we can see, the difference in potential between the pitting and the protection potential is relatively large, resulting into a large hysteresis, indicative of high tendency towards pitting. By looking at the difference between E-Pro and E-Pit, which translates to the size of the hysteresis, it is found that sample A has a larger and more negative difference between E-Pro and E-Pit compared to samples B and C. And as mentioned earlier, sample A is actually 304, where B and C are 316. These are micrographs of optical microscopy micrographs of the samples after 1 day of soaking in the Kokubo solution. And as we can see, there are larger and areas and more pitting in sample A compared to sample B and sample C. As we increase the soaking time of the pits in the Kokubo solution, the amount of pitting is also observed to increase. Now, EDX analysis showed chlorine inside the pits of the samples when analyzed using EDX, and this chlorine, which is present in the SBF as well as in human plasma, results into the autocatalytic pitting corrosion of stainless steel. This is a diagram of the pitting corrosion. The anodic reaction is basically the oxidation of iron to ferrous, releasing 2 electrons. And the cathodic reaction, which occurs at the surface, is the reaction of oxygen with water and electron forming hydroxide. So we have a complete electrochemical cell. Now, as ferrous ions are generated inside the pit, the positive charge in the ion will attract the chloride or the chlorine ion present in the simulated body fluid. It will go inside the pit, and once inside the pit, the chlorine will react with iron, forming iron chloride or ferrous chloride. Now this ferrous chloride reacts with water to form ferrous hydroxide, releasing hydrochloric acid. And this hydrochloric acid again induces an autocatalytic effect in the corrosion, and your pit will continue to grow even if no additional chlorine is added from the solution. So as a conclusion, Steinmann pins are subject to pitting corrosion in human body fluids as recommended by the medical practice. It should only be used for initial fixation. Now, locally available pins may be substandard, meaning 316L is required, but since you as a patient or even the hospital itself has no way of determining its composition, some scrupulous vendors may be substituting 304 stainless steel for 316L, or maybe even just 316, because to the naked eye, you will not be able to tell the difference. As we see, even an XRF is unable to determine the difference, and you need an optical emission spectrometer or more sophisticated analytical techniques. Now, there are no existing domestic regulations. All of these pins come in imported, mostly from China, Pakistan, or India, and we have no quality control over them. So basically, it's just the public beware when you're going to purchase these pins. Now, because the Steinmann pin is still subject to human body corrosion, body fluid corrosion, maybe anti-corrosion coatings such as hydroxyapatites, as well as other organic coatings, may need to be investigated, especially under the local scenario that patients will tend to purchase stainless steel Steinmann pins more compared to the more expensive titanium, aluminum, vanadium alloys. The next steps in the study will be to conduct electrochemical impedance spectroscopy to determine the actual corrosion rates of these materials, but the results of this is for another report. So thank you very much for your attention, and are now ready to entertain questions from the audience.
Thank you very much, Dr. Mena, for your presentation. So just to give a preview for the Don Benito Yao Metallurgical Engineering Award. So the chair donor is from Steel Asia Foundation, which is care of Miss Lilian Yao, which is the executive director of Steel Asia. And she graduated from the BS Chemical Engineering program year 73. Additionally, the chief metallurgist of Steel Asia Manufacturing is METI alumnus Mr. Dodds Cola. So again, thank you, Doc Mena, for your presentation. So the floor is now open for a few questions. So if you have questions, please type in our Q&A portion. Okay, so we have a question here. So given the availability of 304 stainless pins in the market, can you estimate how shorter is the time of use of this type before risking the patient to sepsis?
Um, Thank you for the question. As can be seen from some of the pictures, the onset and rate of corrosion appears to be faster for the 304, but the actual corrosion rates uh, will be the subject of the next report, in which we use EIS to determine the relative rates of the corrosion for 304 versus 316 stainless steel in simulated body fluid.
Uh, Thank you, Doc, for your question. So, was your question answered, Doc Leslie? Okay. We have another question here. So, do you have any idea about the cost comparison between stainless steel 316L and the titanium aluminum vanadium Steinmann pins, which is normally used for, which is normally used?
The price difference between 316L stainless steel and titanium aluminum vanadium alloys as orthopedic implants is about 10 times. So it is quite substantial. Now the price difference between 304 and 316 stainless steel is about 4 times. So as you go up into from 304 going to 316, you're multiplying the cost by 4 times. Then from 316 to titanium, vanadium, aluminum alloys, then it is increased by 10 times or 40 times against 304. So the cost differential is quite substantial, which is why a lot of people stay with the 316 and stay with it longer, although the um, application times are supposed to be limited. Um, there is a question from Tito Aliga asking that we may be able to link up with the Orthopedic International making ortho implants. Jude Sassing, by the way, Sir Tito, was my student in material science, and their quality director, Cha Gorobat, is actually our MS student in material science and engineering, and she's looking at the corrosion of titanium, aluminum, vanadium alloys as her thesis.
Thank you so much, Dr. Mena. So, are there any other questions from the body? So, Doc, I have a question on the corrosion type. So, for this particular study, only pitting corrosion was presented. Were there any types of corrosion that was observed during the experimentation?
Only pitting corrosion was observed, Joy, and pitting corrosion is basically the critical failure mechanism for stainless steel alloys.
Thank you so much, Doc. If we have no more questions, there's one question here. From Sir Stan Ehera. So, Doc, given these results, would this be a sort of call to action to establish local standards for Steinmann pins if these are not already established by the BPS?
Yeah, definitely, Stan. Not only for Steinmann pins, but for all orthopedic implants. We basically have no control, and even the hospitals do not want to get involved, because if they get involved, then they become responsible. So really, the patient is asked to buy whatever he likes to be uh, used by the orthopedic surgeon, and the orthopedic surgeon is not responsible for whatever the side effects are.
So I think we have time for one last final question. So this is from Dr. Leslie Joy Diaz. Do you think crevice corrosion can also be possible?
The The primary mode, actually, Doc Les, is pitting corrosion, because crevice corrosion occurs when you have portions of the steel being covered or starved from oxygen, and that does not happen in this application.
Thank you so much, Doc. So, if since we have no more time for questions, let us now proceed to our next speaker for this session. So, thank you so much, Professor Manolo Mena. So, our next presentation for this session is entitled Fabrication of Cellulose Acetate-Based Radiation Grafted Anion Exchange Membranes for Fuel Cell Application. So this is for the MECCAT Professorial Chair Award, wherein the Professorial Chair donor is CE alumni of year 1994, Mr. Michael Alan Sica. So our presenter for today is Dr. Richard D.V. Espiritu. Dr. Espiritu has obtained his PhD in Chemical Engineering and Advanced Materials from Newcastle University in 2017. He has established his own research group, the Polymer Materials for Energy Research Laboratory, or Polymer Lab. Dr. Espiritu has honed his expertise in anion exchange, membrane fabrication via radiation, grafting technique, and has published a total of 10 papers to date and has a pending utility model. So it's my pleasure to welcome our next speaker for this session, Dr. Richard D.V. Espiritu.
Good afternoon, everyone. I am delighted to have this opportunity to present to you my research topic titled Fabrication of Cellulose Acetate-Based Radiation-Grafted Anion Exchange Membranes for Fuel Cell Application for the MECCAT Professorial Chair Award. My name is Richard Espiritu of the Polymer Materials for Energy Research Laboratory of the Department of Mining, Metallurgical, and Materials Engineering. As a brief introduction, a fuel cell is an electrochemical device that converts chemical energy into electrical energy. Essentially, a fuel cell can be classified either in terms of their electrolyte or in terms of the temperature for which they are normally operating. An alkaline fuel cell is wherein OH ions are involved in the electrochemical conversion. You have an anode, you have a cathode, and you have an electrolyte or the membrane in between these electrodes. Oxidation takes place at the anode, which means to say you will lose an electron. And it is possible by wherein your OH ion reacts with the hydrogen fuel, producing water and that of the electrons that goes out through an external circuit. And after that, the electron goes back or goes to the cathode, wherein reduction takes place. Your electrons join with the oxygen and that of the water produced from the anode to produce your OH ions, and that is where the cycle continues. Our country is aggressively embarking on renewable and sustainable energy technologies in order to address our increasing demand for energy. And the use of locally available cellulose resource that we have here in the Philippines will translate to cheaper membrane electrode assemblies. A radiation grafting technique is envisaged as a facile method of producing cellulose-based anion exchange membranes, and this facility will be provided by the Philippine Nuclear Research Institute. So using this available cellulose resource as a precursor for the membranes that we will produce, the research aims to fabricate cheaper membrane electrode assemblies, which will of course cascade to lower cost of fuel cell modules. For the membrane synthesis, cellulose acetate film precursors are immersed in a screw cap vial with 31:26:43 bi-volume ratio of vinylbenzyl chloride, toluene, and methanol solution. after which the vial will be subjected to gamma radiation using cobalt-60 source at different radiation doses. Then, the grafted copolymer is then subsequently subjected to functionalization, wherein the copolymer is immersed in trimethylamine for 72 hours. In terms of membrane characterization, the following properties are what we need to assess on the fabricated membranes. First is the degree of grafting. This is the measure of extent of polymerization expressed in terms of percentage mass of the grafted component with that of the polymer matrix. Another one is the degree of acetylation. This would give us an idea whether the cellulose acetate we used is a monoacetate, a diacetate, or a triacetate. The ion exchange capacity is also a very important metric of membrane properties, and this is the measure of the ability to displace or transfer OH ions within its structure. Of course, hydrophysical property should be measured as well, the water uptake, the hydration number, and of course, the degree of swelling of the membrane. In terms of composition assessment, we will use FAR, that is to verify the grafting as a successful functionalization of our membrane, and of course, thermal stability using a thermogravimetric analyzer. A very important measure of membrane performance would be its ionic conductivity. This is performed using an in situ fuel cell setup in the University of California, Merced. What is shown on your screen is the FTIR spectra of the cellulose acetate film, the grafted CA-VBC copolymer, and of course the TMA functionalized CA grafted VBC copolymer. So, checking on your original CA film, you would expect that it will exhibit characteristic peaks to that of your CA. You have the carbon double bond to the oxygen stretching due to the ester functional group at 1735. You have signal at CH deformation vibration at 1367. And of course, you would have the methyl rocking vibration at 1031. Then, successful grafting, of course, with VBC of your CA film would exhibit additional peaks associated with that of the vinyl benzyl chloride. You would see the carbon-carbon double bond at 1488 to 1476. That's stretching vibration due to the presence of the aromatic ring. And of course, you would have the 708 stretching vibrations of the carbon chloride bond and the CH vibration at 893, at 813 per centimeter wavelength associated with the aromatic group. And lastly, the successful functionalization with trimethylamine of your copolymer is shown. So you would see that there's a strong peak of stretching vibrations at 3334 per centimeter wavelength, okay, associated with the TMA. And then you also have nitrogen methyl deformation at 15 to 1350, the nitrogen methyl rocking vibration and carbon-nitrogen stretching vibration at 1200 to 100. As you can see, you lose the 708 peak. Okay, you don't have the 708 peak here, which means to say it's an indication of successful exchange or successful functionalization of the amine to that of the position of your chlorine ions. The degree of acetylation is determined by integrating the area of the acetyl group and that of the hydroxyl group in your FTIR spectra using an Origin Pro software, after which the ratio of the acetyl group to that of the total is computed so that you would have an estimate of the degree of acetylation. Based on our calculation, the degree of acetylation is 2.5, which means to say that the cellulose acetate films we used in this research could be a diacetate or a triacetate, considering that the degree of acetylation is in between 2 and 3. The degree of grafting is the measure of the amount of vinyl benzyl chloride that has successfully attached to or grafted on to your cellulose acetate film. And as you can see from the table, for each initial CA film thickness, the degree of grafting increases with the radiation dose rate. This is expected because as the radiation dose is increased, there are more high energy radiation capable of forming active sites wherein your vinyl benzyl chloride will attach to. The ion exchange capacity is very much dependent on the degree of grafting of a particular membrane. So, expectedly, the IEC increases with your DOG, which increases with increasing radiation dose. The theoretical IEC is expected to be higher than that of the experimentally measured IEC. This is because the theoretical IEC assumes complete quaternization of VBC with that of DMA and assumes complete ion exchange between OH ions and that of chloride ions. The obtained values of IECs experimentally is a good measure of its expected ionic conductivity performance. So, the higher the IEC, the higher ionic conductivity that we expect because it has a higher measure of its capability of transferring or displacing OH ions with that of each particular functional group in our membrane structure. The hydrophysical properties of the membrane in terms of its water uptake, hydration number, and membrane swelling are also very important to assess. This is because even though it is desired that the ion exchange capacity would be high, which will translate to a higher ionic conductivity, it is expected that at high IEC, the water uptake, the membrane swelling, and the hydration number would be high as well because it would be a measure of how much water is present, which means to say it would be a measure of how much OH ions could be transferred or displaced in that particular structure. So even though we want high IEC so that we have high ionic conductivity, we need to balance this with the structural integrity of the membrane so as it will not swell too much or it will not absorb much water, especially wherein our membranes will be sandwiched in between the two electrodes. It is also important to ascertain the thermal stability of our membranes, particularly in prolonged operating service conditions. The TGA thermogram under that of nitrogen gas and also that of under oxygen, since oxygen is the common fuel or oxidant in the cathode, okay, both plots show that the onset temperature is way above 100 degrees Celsius. For that of under nitrogen, it's about 188 degrees Celsius. And with that under oxygen, it's at about 190 degrees Celsius. So these onset temperatures would provide us evidence that the fabricated membranes are thermally stable within the low temperature operating regimes. Lastly is the ionic conductivity, which is a measure of a fuel cell membrane performance. As you can see from the plot, the ionic conductivity essentially increases with increasing temperature. We have tested 3 of our membranes and compared it with the commercial Tokuyama E201 an ion exchange membrane. So for the B40 and the B31 membranes, these are membranes prepared at high radiation dose rate. Well, expectedly, their DOG is high, their IEC is high as well, reflecting high ionic conductivity. However, due to its very high IEC, the membranes tend to disintegrate or fail mechanically at 60 degrees Celsius. The best candidate so far is the B25 membrane prepared at a lower radiation dose rate hence a lower IEC, but the ionic conductivity profile is comparable with that of the commercial Tokuyama A201 membrane. This provides the proof that our fabricated membranes, even at a lower IEC value with that of a commercial Tokuyama A201, would perform comparable in terms of its ionic conductivity. So as a summary, this research was able to successfully fabricate novel cellulose acetate-based anion exchange membranes utilizing radiation grafting method. The highest degree of grafting we have obtained was about 45% with corresponding ion exchange capacity of 2.1 millimoles per gram. The TGA thermogram also proved the stability of our membranes at 100 degrees Celsius, which is below that of the normal operating temperature for fuel cells. We were able to fabricate B25 membranes, which is the best so far, exhibiting ionic conductivity comparable with commercial A201 Tokuyama at even lower IEC. And the focus of our future research would be the fabrication of the AEM, focusing on optimizing the balance between the ion exchange capacity and its resulting hydrophysical properties to the target ionic conductivity. I would like to express my gratitude to the Philippine Nuclear Research Institute for their irradiation facility and for Professor Abel Chuang of the University of California, Merced, who tested my membranes in their fuel cell test station, of course made possible by the PICARI program. Also, the UP OBPAA ECWRG project, and most importantly, to the MECCAT professorial chair that made this presentation possible. Thank you very much, and if you have any question, I'll be happy to answer them.
Thank you, Dr. Chard, for that presentation. So the floor is now open for a few questions. So we hope that the body would ask their question in our Q&A dashboard. So there's a question from the body. How about the surface area analysis of the synthesized samples? Why was this not conducted?
Okay, it's not really clear on the question of what the person asked. Want me to look into onto the surface, right? So maybe maybe the question is about the morphology of the surface. We were able to gather the electron micrograph, but we were actually trying to utilize Raman spectroscopy. It's just that we had difficulty looking for an available equipment because the Raman spectroscopy, particularly the microscopy of Raman, could provide us the contours and that of the surface morphology, or how good would be the grafting on the surface and also at the bulk. So what's really important for the membrane to be characterized is in terms of its electric or ionic conductivity through the membrane. It's not really on the surface. So it is interesting to look onto the surface, but we're pretty much more interested into the property of the bulk.
Thank you, Dr. Chard. So I hope this has answered your question. So we have another question. So is it correct that B25 AEM degrades at 80 degrees Celsius based on one of the plots that you have shown? If yes, is there anything you can do to overcome this and be at par with Tokuyama type, and is this necessary?
Okay, the onset temperature of 180 to 190 is the temperature at which the cellulose acetate by itself starts to degrade. But the the particular temperature at which it degrades would be different now because it is grafted with another component. So it has a VBC on it, wherein the aromatic provides stability to the structure of the CA. And also, as I mentioned earlier, the 180, 190 temperature is way above the normal operating temperature of a fuel cell, which is just about 60 to 100. So it's actually more than double. So the integrity or the thermal stability of the AEMs fabricated using this method is definitely ascertained. Masyado nang mataas, or it's the 188 to 190 onset temperature is way too high, way above the normal operating temperature.
Thank you so much, Dr. So we have another question here. Your study used diacetate form of cellulose acetate to prepare the membrane. What could be the effect of using cellulose acetate with different degree of acetylation? Say monoacetate or triacetate to the resulting property of the fabricated anion exchange membrane?
Okay, so that's an excellent question, because clearly in our research, we only prepared membranes from a single source of cellulose acetate, and this is diacetate based on our calculation of the degree of acetylation. And indeed, there will be an effect on the property of the resulting AEM if we use cellulose acid precursors with different degree of acetylation. And we know that a monoacetate is essentially hydrophilic compared to that of triacetate or diacetate, which are both hydrophilic. So essentially, hydrophobic rather. So essentially, the measure of hydrophobicity increases with the degree of acetylation. However, if we use triacetate, for example, there is the bigger chance that all these functional groups would then be grafted with VBC. So making the triacetate, which is hydrophobic, to be hydrophilic once it's grafted. So it's the issue not really is whether you use a mono, a di, or an triacetate, but it is how you control the degree of grafting, how much grafting you impart to the cellulose acetate, and how you will be able to control the functionalization, because essentially what you will end up with will be the IEC value. And too much IEC will cause the membrane to swell too much. That's why you have to balance the degree of grafting and that of the resulting ion exchange capacity.
Thank you so much, Dr. So the floor is still open for a few questions. So before we entertain the question, we have a comment here from Sir Tito of UP ERDV. I hope you are collaborating with DCHES Electrochemical Lab and Triple EI's lab, which will produce a UP battery to usher in our Diliman Valley Tech Complex.
That is correct, sir. That is correct. Well, I am in close contact or in close collaboration with Joey, Dr. Ocon, because his work is on batteries. So essentially, I'm a fuel cell. I produce electricity. I'm into the energy production, and the storage would be Joey's part. So we are really in close collaboration for the research on renewable energy technologies for UP Diliman.
Okay, so I think we have time for one last question. So in terms of the Philippine setting, have you discussed with any local company who may be eventually commercializing this?
Oh, okay. So currently we have a pending utility model claim with UPTT BDO. And after I obtained that it is, I think, the more proper time so that I would have a better footing in collaborating or in talking with prospect companies with regard to the membranes that I will be producing.
There's more of invitation question here. So this is from Dr. Zubi Montserrat. So I work with the CA membrane. Are you open for collaboration?
Oh, yes, definitely. Hi, Sir Juby. I was about to make a chat with you as well because we worked before. I think we we shared some courses in the graduate level, and I know Sir Juby definitely. Well, I'll get in touch with you after the presentation. Definitely excited to work with you.
Okay, so if there are no more questions, I would like to thank Dr. Richard Espiritu for his presentation. So thank you so much, Dr. Chard. So now we move on to our next presentation. So our next presentation is entitled Project Daluyan, Water Quality, Hydrology, and Hydraulic Analysis of Boac River in Marinduque. So this would be presented by Assistant Professor John Kenneth A. Cruz. So Sir Ken graduated as magna cum laude in his BS Materials Engineering, and he has a master's degree in Material Science and Engineering from UP Diliman also. In his 10 years of service, he has served as the Outstanding Engineering Instructor. He has received the Outstanding Engineering Instructor award for the College of Engineering in 2015. Sorry. He has published 5 papers with topics mostly on wastewater treatment in international journals. He has also helped establish materials for art, design, and engineering laboratory, and has headed the research projects such as Project Daluyan and Deep Bio Inc. So this presentation is for the Crisostomo A. Ortigas Professorial Chair Award, wherein Dean Crisostomo Ortigas Chair is funded by the UP Alumni Engineers Association. So the president is a UP ERDP member, Sir Elmir Cruz Dipil, which is an IE graduate of year 92, and the ed is Dr. Eric Tingatinga. So everyone, it's my pleasure to present Sir Ken's presentation for this session.
Good afternoon, everyone. I am John Kenneth Cruz from the Department of Mining, Metallurgical and Materials Engineering, and I'll be presenting the Crisostomo A. Ortigas Professorial Chair Lecture for our study entitled Project Daluyan, Water Quality, Hydrology, and Hydraulic Analysis of Boac River in Marinduque. This study was conducted with my students, Jaime Baquiran Jr., John Kenneth Suwan, and a colleague from the Institute of Civil Engineering, Assistant Prof. Jaime Bren Villalba. Boac River was one of the major sources of livelihood and food for communities, especially near or along the river. However, the 1996 Copper mining disaster happened, which spilled millions of tons of toxic mine wastes along the river, which led to it being eventually declared as a biologically dead body of water. Standards such as the Dow 2016-8 provide a water quality guideline on specific parameters that bodies of water should have. Considering that no comprehensive rehabilitation was conducted along the river, it is thus imperative to continuously monitor and perform characterizations for the river to be fully analyzed for rehabilitation and other policymaking. Thus, our objectives are first, to compare the water quality of samples obtained from Boac River to water standards. We also aim to determine presence of metal ion contaminants in the river, if any, perform hydrological analysis on the Boac River to identify catchment contributing to a sampling point, and finally, we intend to calculate the flow velocity as the hydraulic parameter. The first in our methodology is the identification of sampling points, which in this case, we were aided by the Environmental Office of Marinduque. We have identified 4 sampling points. The first one, which is the Hinopulan area, is the upstream most that is accessible to us. We have 2 midstream points, namely Pagsangahan, which is located in Barangay Canat, and Balimbing. And finally, the most downstream point, which is located near the mouth of the river, is is the sampling point in the Tabique area. These are photos taken during our fieldwork and sampling. Okay, so for the first objective, which is to compare the water quality of our water samples, we conducted 24-hour sampling and monitoring with 4-hour interval. So we conducted this 8 a.m. the first day up to the 8 a.m. the next day. So sampling was done last November 20 to 21 and November 23 to 24 in 2019. Grab sampling was done at the middle of the river to obtain a representative sample. On-site measurements were taken for parameters such as pH, conductivity, and temperature. We also determined the surface flow velocity, which will be used later on in the fourth objective of our study. For the second objective, which is determination of presence of metal ions, we acidified and preserved the waters obtained during our monitoring fieldwork. So the laboratory test was conducted using ICP-OES to determine the presence of heavy metals as well as the concentration of these metal ions. For the third objective, which is to perform hydrological analysis on Wawak River, we need to define some key terms. So hydrology pertains to the interaction of water with its environment. So it also pertains to the distribution of water in a system. So for example, this map shows a general hydrology of the river. So we know that water can flow from high elevation, and it's actually collected at the basin, which is in this case, it's the river. A watershed is the total area that contributes to the entirety of the river, whereas a catchment is the area that contributes to a specific point only. Okay, so the watershed and the catchment area may be interchanged or are actually equivalent if our point of interest is the point at the mouth of the river. So for this study, all simulations were generated using QGIS version 3.12.1 software. And finally, for the fourth objective, which is to calculate flow velocity as hydraulic parameter, on the other hand, pertains to the movement of water, especially how fast the water moves in our system. So for our study, we used a float method, which utilizes a floater. In this case, we used a ping pong ball attached to a rope with known distance, with known length. Okay, so and we monitor the time it takes for the whole length to be taut. So the flow velocity is calculated as the length of the rope over the time it takes for the rope to lengthen. So please take note that what we're measuring here are only surface flow velocity. Okay. Also in the hydrology, we're only measuring the surface water moving from the catchment basin into the river. So for our results and discussion, we'll start with the basic water quality parameters. Presented here are box and whisker plots of the different parameters at different locations. The red lines here indicate the limit values for a specific standard. Okay, so let's start with the pH. The average pH values are well within the standards. In fact, these average values are close to neutral, with the highest being in Tabique at only at 8.0. Okay, so based on the Dow 2016-08, these pH values are acceptable for Class C waters. On the other hand, for the temperature measurement, average values are well within the standards, okay, except for some outlier values both in Pagsangahan and in Tabique. And finally, we have the conductivity measurements. The upper red line here indicates the maximum limit for conductivity according to the EPA standard. So as we can see here, the conductivity values are quite above the threshold. Okay, so with the measurements in Tabigue being the more dispersed compared to those in Hinapulan, Pagsangahan, and Balimbing. This may be attributed or can be attributed to the fact that Tabigue is located near the mouth of the river and thus it's highly affected by tides. In terms of water hardness, which in this case is presented as ppm of calcium carbonate and evaluated using this equation. Okay, so the concentration of calcium and magnesium are actually results from the ICP characterization. So again, these box and whisker plots show that our values are above the 180 ppm. Water along Bowak River may be classified as very hard. Also obtained during the ICP OES characterization are the presence of these heavy metals as well as their concentrations. So these values, the highlighted cells are actually those values exceeding the concentration limit which were indicated in this last column. Okay? So it's worth noting that copper, lead, and mercury consistently exceed the upper limit. Okay. Arsenic and manganese were relatively high in some areas. Only iron has concentrations below the acceptable limit. So it's worth noting that arsenic, lead, and mercury are listed as among the toxic heavy metals, especially in their dissolved form. Mercury can cause spontaneous abortion, congenital malformation, and gastrointestinal disorders. On the other hand, lead may cause dysfunction in kidney, reproductive system, liver, and even brain. Arsenic is also one of the highly toxic metals in terms of mortality and morbidity rate worldwide. And finally, excess copper can cause hemolysis, kidney damage, and a number of cases of influenza syndrome. And thus, it's very important to really continuously monitor the water quality of the river, because a lot of the members of the community still pass through, still interact with the waters along the Bowak River. For identification of the catchment or calculation of the catchment area along the Bowak River, so we calculated that the Hinapulan catchment area covers land area of 61.76 kilometers squared. Okay, so that's this area. When we proceeded with Pagsangahan, we now cover the veins from the northern portion and the southern portion. So the total area coverage significantly increases. So at the Pagsangahan sampling point, okay, so the total area that contributes to the river is around 150.16 kilometers squared. Moving to our next sampling point, which is Balimbing. Okay, so the total area now is 191.55 kilometers squared. And finally, the Tabigue catchment area, which also corresponds to the watershed area, is around 214.278 kilometers squared, covering 6 municipalities and 22 barangays. It's worth noting that the now closed San Antonio Pit and Tapian Pit are part of the Hinapulan catchment basin. If these pits overflow, they can still contribute to the water quality of the river. And finally, for hydraulic characterization, which we calculated the time it takes for water to move from point 1 to the mouth of the river. So using QGIS, we were able to calculate the segment length, okay, and average flow velocity were obtained during monitoring and fieldwork sampling. So we were able to calculate the time it takes to cover the specific distance. Now, determining the average time it takes for water to travel a certain distance is important, because since water can contain specific contaminants, we also want to know how long can these contaminants travel along the river, assuming that they maintain in the water and do not undergo other processes such as precipitation or absorption along the sediments. In conclusion, the recorded pH and temperature values are well within the acceptable water quality for DNR Class C waters, while the average values are above the ideal conductivity levels based on the EPA standard. Water samples along Boac River as classified as very hard waters based on the concentrations of calcium and magnesium. Copper, iron, arsenic, lead, manganese, and mercury are present along the river, with copper, lead, and mercury consistently displaying values above the threshold limit. The Boac watershed covers a total area of 214.278 kilometers squared that covers 22 barangays in 6 municipalities. And finally, the calculated time for the river flow to cover a distance of approximately 22.86 kilometers is around 12.558 hours. For our future work, we want to compare the water quality at the confluence point, which is specifically is located at the Pagsangahan sampling point. Okay, so we want to monitor the water quality in northern segment of the river versus the southern segment of the river. Further studies also include characterizing the size and composition of sediments along the river. This can help us understand whether these metal ions are coming from the sediments or these metal ions can absorb to the sediments and eventually be transported to different parts of the river. This study would not have been possible without the help and support from the local government of the UK, especially the Office of the Governor, the PGNGO, and the barangay offices. Special thanks are also extended to the MASEC as well as to the Canosa family for really helping in our study. Funding was provided by the Crisostomo A. Ortigas Professorial Chair, as well as the BL Gozon Thesis Grant of J.K. Suan and Jaime Bakira. And we also thank the laboratories where we conducted our experiments in the Composite Materials Research Lab and Environmental Engineering Lab. These are our references, and thank you for listening.
Thank you so much, Sir Ken, for your presentation. So now the floor is open for your questions. So we have a few questions here in the floor. We have a few questions here. So the first question is, have there been manifestations in the health of the community due to the high content of the toxic metals? So there's a follow-up question. So ito muna po.
Thank you so much. Good afternoon, everyone. So far, may mga claims, there are claims from the community that they feel they have this certain disease, and it's probably they're pointing that these are caused by their exposure in the river. However, we do not have a definitive answer and characterization with a medical professional so far. So we really cannot ascertain whether the symptoms that some of the community members are like the community members experience were actually due to their exposure to the Boac River.
Thank you so much, Sir Ken. So the follow-up question is, was this study shown to the LGU, and is there any plan of action?
Okay. So I'm finalizing the report to be submitted. So the report that I'm to submit to the Environmental Office of Marinduque is more comprehensive. That's why it's taking me a longer period of time to write. But yes, we are communicating with the LGU. So far, they have speculations and they are aware that the metals exist in the river. However, they really do not know the extent of the condition yet. So, and in terms of plan of action, we don't know yet, but they're really asking for help, expertise, if we can offer them assistance on how to move forward with possible rehabilitation of the river or any other action for that matter.
Thank you so much, Sir Ken. So I will rearrange the order. This is also related in the previous question. So What are the current uses of the water in the Boak River? And have you tried informing the local environmental engineers or public health officers?
During our time that we uh, did our field work, so the Boak River is currently being used as some segments. They are quarrying the sediments which they use for the construction of their roads. And in some areas, uh, it's being used for domestic purposes, particularly sa paglalaba, ganyan. But it's really makikita natin that tumatawid pa din yung mga tao doon sa river. In terms of informing local environmental engineers and public health officers, we are directly connected with the PGNRO, which is the Provincial Government Environmental and Natural Resources Office of the Marinduque, and yeah, we're really in constant communication with them, and I'm about to submit the report for them.
So, thank you, Sir Ken. So, I think we have these two related questions. So, sabay ko na lang po itatanong. Would you consider taking samples in different seasons? And also, why only conduct sampling in November? Won't the transport be affected by hydrological seasons too?
Okay. So for the first question, which is taking a sample at the different season, we're supposedly scheduled to do another fieldwork last March. However, due to COVID, that was March to April. However, due to COVID, we were not able to pursue the additional sampling. And yeah, that's really part of the objective, to compare the seasons. And actually, the 2 dates that we used were to compare between the weekday and the weekend. But so far during our analysis, there was no significant difference between these 2 days. Sorry, what's the second question?
The follow-up question was why conduct so in November, and won't the transport be affected by hydrological seasons too? So if you have wet or dry seasons.
Yes, the weather in Marinduque, actually the peak of the wet season in Marinduque is November, and we also plotted the peak of the dry season, that's around March and April. So that's the original intention. And yes, it's highly affected because during the dry season, some parts of the river dry up. Okay, so and yeah, based on the stories, based on our conversations with our contacts there. So yeah, it will be really affected by the season. And it's very good, really, it's quite good to see the whole picture. However, due to our limitations, we cannot proceed with the second part of our study.
Okay, so there are additional questions. So why did you only measure surface velocity? Why not measure velocity on 60% of total depth, which is the typical way?
Yeah, we consulted with Ma'am Aimee, which her expertise is also on hydro. She's from the Institute of Civil Engineering. And yes, the typical practice is to do the 60% total depth. However, we need specific, there's a specific tool to accurately measure the depths at the velocity. So when we consulted with Ma'am Aimee, she mentioned that we can at least approximate the surface velocity. Of course, all the calculations and all the simulations done are affected by these limitations.
Thank you so much, Sir Ken. So I think we still have time for additional questions, just in case we run out of time. So Sir Ken will answer your question in the Q&A portion. So there's a question here on Boak River has been considered dead for a long time, but are reports that fish and ducks are usually thriving in it. Did you observe the same during your visit? And do you have suggestions on technologies that can be used to improve the water quality of the river?
Okay, in terms of presence of fish, yes, we observe specifically in Hinupulan, we observe some very small fish in the area, very small and quite a few fish in the area in Hinapulan and in Pagsangahan. However, towards the downstream area, there's really minimal biological activity. And in terms of the suggestions on technologies, we can have two approaches on the implementation of technology, but actually the NSTP team of the College of Engineering all tried to visit and interacted with the locals. And we feel that the best approach would be to solve the problem by empowering the community. So we we have collaborators from CSWCD, and she mentioned that longer lasting solution should come from the community, and we as members of the academe and researchers should help the community find and implement possible remediation techniques to help improve the quality of Bowac River. So yun po.
Thank you so much, Sir Ken. So unfortunately, we have run out of time. So I would just like to mention one comment of Sir Tito on possible collaboration, so with DENR, and especially on the penalty imposed on Marinduque mining. Sir Ken will be answering your questions in the Q&A portion. Thank you so much, Sir Ken, for your presentation.
Thank you, ma'am.
So now we will move on to our last presenter for this particular session. So our last speaker for this session is to be given by Assistant Professor John Lowell P. Bukis. Sir Jolo is a licensed metallurgical engineer, and he has obtained both his bachelor's and MS degree in metallurgical engineering in UP Diliman. He has conducted comparative studies on various adsorbents that could remove heavy metals in leachates derived from the mine tailings in the Hokkaido University. His other research interests include microstructure development, metalworking, and failure analysis. So his presentation for today is entitled Removal of Copper Ions from Synthetic Wastewater Solutions Using Ipil Seeds. So this presentation is for the Marie Gerbeau Professorial Chair Award. So the Marie Gerbeau Professorial Chair donor is ERDFI member Vic Munoz, which is a METI alumni of year 63. So everyone, let's welcome our next presentation by Sir Jolo.
Good afternoon. Today I'll be talking about the removal of copper ions from synthetic wastewater solutions using ipil seeds. This study was conducted in cooperation with undergraduate students Mr. Joshua Dulay and Mr. Vince Fernandez as part of their undergraduate research project. For the flow of the presentation, I'll first talk about a brief background of the study, the methodology employed in the experiments, the important results and highlights of the discussion, and to summarize everything, we have the conclusions. Oxidation of the sulfide minerals from reactive mine tailings may lead to acid mine drainage. The release of sulfuric acid, along with heavy metals such as iron, copper, and arsenic, may contaminate soil and groundwaters. High concentrations of these heavy metals are dangerous to the environment and to human health. Various methods have been developed to treat wastewaters, one of which is the biosorption of heavy metals using agricultural waste such as coffee husks, rice husks, mango peels, ipil pods and seeds, to name a few. These materials are cheap and readily available, which make them viable candidates to develop as solvents. The primary goal of this research is to remove copper ions from synthetic wastewater solutions using ipil seeds. It also aims to determine the adsorption behavior at various initial ion concentrations and varying contact time. Lastly, it also aims to explain the adsorption mechanism using kinetic models and isotope models. For the biosorbent preparation, ground ethyl seeds were soaked in 0.1 molar sodium hydroxide. The seeds were then filtered and dried in an oven set at around 80 degrees Celsius for about an hour. For the batch adsorption test, 30 ml of the copper stock solution was mixed with 60 mg of the biosorbent. The pH was then adjusted to 3.6 using 0.01 molar sulfuric acid. The solutions were then placed in an orbital shaker set at around 100 RPM. Sampling was done at various time intervals. The solutions were then filtered and the copper content of the filtrates were determined using XRF. The initial copper concentrations were set at 50, 75, 100, and 125 ppm, while the contact time varied from 5, 15, 30, 60, 180, 360, and 720 minutes. The adsorption kinetic models were used to describe the mechanism of the process. The adsorption capacity QT was determined using equation 1, wherein Ci and Ct are the initial and the instantaneous concentration of the adsorbed metal, V is the volume of the solution, and M is the mass of the adsorbent. The pseudo first order kinetic model is described by equation 2, where in case of 1 is the rate constant, and QE is the equilibrium adsorption capacity. The pseudo second order kinetic model was also used as expressed in equation 3, where in case of 2 is the rate constant. Lastly, the Elovich equation as presented in equation 4 was also used. Alpha is the sorption constant and beta is the desorption constant. In addition to the kinetic models, the data was also fitted against various isotherm models. The Langmuir isotherm as described by equation 5, where Q0 is the maximum monolayer coverage capacity, C is the equilibrium concentration of the adsorbate, and K sub L is the Langmuir constant. The Freundlich model described by equation 6, 1 over N is the adsorption intensity, and K sub F is the adsorption capacity. The Dubinin-Nerduskevich or the DR model was also used as described in equation 7, where KDR is the constant. Lastly, the Temkin model as described by equation 8 was also used, where A sub T and B sub T are the associated constants. The adsorption capacity was plotted against time at various initial ion concentrations. We can see from the figure that the adsorption capacity increases with longer contact time. The adsorption capacity rapidly increased within the first 60 minutes, then slowed thereafter. The rapid increase in the adsorption capacity at the early stages is due to the high number of active binding sites available at the start. The number of the available binding sites decrease as the adsorption process progresses. This leads to the decrease in the rate of increase of the adsorption capacity. The highest adsorption capacity values were determined to be at around 720 minutes for all initial ion concentrations. And beyond the 720-minute mark, there may still be a significant increase in these values. For the effect of the initial ion concentration, looking at the data at around the 720-minute mark, the maximum adsorption capacity of 21.1 mg per gram was determined at around 50 ppm. We can also see that the adsorption capacity decreases as the initial ion concentration increases. This is due to the limited number of active binding sites at a constant biosorbent dosage. The correlation coefficients of the various plots for the pseudo first order, pseudo second order, and the Elovich equation are shown in this table. From this table, we can see that the data best fit the pseudo second order model at all initial ion concentrations. The pseudo second order kinetic model parameters were then determined. From this table, we can see that the rate constant, K sub 2, and the initial absorption rate, H, are highest at 50 ppm. Results also show that the rate constants and the adsorption capacity decrease as the initial ion concentration increases. Reactions that fit the pseudo second order kinetic model are described by a 2:1 adsorbent site adsorbate ratio. On the other hand, the adsorption isotherms are presented as follows. From the correlation coefficients, we can see that the data best fit the Langmuir isotherm model. The Langmuir parameters were then derived. The maximum monolayer coverage capacity was determined to be around 11 milligrams per gram. Using the Langmuir constant K sub L, the separation factor R sub L were then determined for each initial ion concentration. Based from these values, the R sub L is less than 1 but greater than 0, indicating that the sorption process is favorable. The Langmuir model also indicates that the copper ions form a monolayer on the surface of the active binding sites. The adsorption process stops when these layers are formed. The Temkin parameters were also used to determine the adsorbate and adsorbent interaction. The heat absorption, B sub T, with a value of negative 0.35 kJ per mole tells us that the adsorption process is endothermic and probably physical in nature. In effect, weak van der Waal interactions adhere the adsorbate with adsorbent. This leads to relatively weak adsorption energies. In summary, the adsorption capacity increases with increasing contact time and decreasing initial ion concentration. The data best fit the pseudo second order kinetic model. The adsorption rate decreases as the initial ion concentration increases. Based on the Langmuir model, a monolayer of copper ions are formed on the adsorbent surface, and the desorption process is favorable. Lastly, based on the Temkin parameters, the adsorption process is endothermic and physisorption is significant. At this point, I would like to thank the donors of the Mare Federal Professorial Chair for their continuous support on the research efforts of the College of Engineering. This concludes my presentation. Thank you for listening.
Thank you so much, Sir Zolo, for your presentation. So the floor is now again open for a few questions for this presentation. Okay. My first question is, have you tried the characterization of the epil seeds on how it can adsorb the copper 2 plus ions into from the solution?
In terms of the characterization, there were previous studies that have already done that, in which the cellulose of the epilipid has an affinity to bind the heavy metals. But for this particular study, we focused more on the actual removal of the copper ion.
So while waiting for, so we have a question here. Can you share your motivations in using epil seeds as an adsorbent material?
Well, the one of the research thrusts, of course, of the department is the development of these kinds of materials in which that are particularly environmental friendly. So the epil seeds are usually treated as waste. So and they're readily abundant. So that's basically the main motivation of using those particular seeds, since they are abundant and then cheap. What if we find other use for it, especially when and apply it to our current problems?
Okay. So the next question is, do you have any motivations on using the same material for adsorption of other heavy metals? So were there references that made use of materials such as epil seed for other heavy metal adsorption?
For other heavy metal adsorption, as the presentation showed before, some used coffee husk for lead, some used rice husks for zinc, some agricultural waste are used for iron. In furthering this study, so one of the plans is to, of course, use it on other types of ions. and then for a single element analysis, and then if after doing the single element analysis, we add it with copper, and let's say for plan to use it on iron, then the combination of iron and copper, and what happens then. So and see what would be the effect of the other ions, if there will be interference in terms of the absorption capacity.
So I think this question is related, so I will just reiterate it again. So Assistant Professor John Lowell, if we apply this on nature, won't the other ions interfere with the bioadsorption capacity of the ipil-ipil seeds? Hello?
Yes, as I mentioned before, right now, what we're able to do is only for copper. So we'll see how it will respond to iron or other ions, and then it will also see how it will fare if it's on a multi-ion system.
Okay, so thank you so much. So we have two related questions here. What is the ratio of the ipil seeds and the copper adsorption in the solution? And the next question is, how much ipil seeds do you need per cubic meter of water?
For this ratio of ipil seeds and copper, it's basically 60 milligram of ipil seeds, and in terms of copper adsorption, let me just check. So in terms of the ratio of the adsorbent to the adsorption capacity, 60/11. So that's around 60/11. That's around 5:1.
So the follow-up question is if you would relate it with the volume of water needed. So how much ipil seeds do you need per cubic meter of water? The assumption here is you have, I think, your wastewater.
Is one the ratio, the solid to liquid ratio is around 60 milligram per ml. So it's around 60 milligram of adsorbent per 30 ml of solution or wastewater.
Right. So there's an additional question here. So I think we have more time. So what are the implications of your finding that the reaction is endothermic?
One would be temperature, maybe a factor that needs to be considered. And another one is that since usually phase absorption is characterized by an exothermic reaction, and then what we found out was that it's endothermic, then there may be other possible reactions occurring on the surface of the biosorbent or during the adsorption process.
Okay. So the next question is, aside from cellulose as your binding effect of ipil-ipil, what specific bioactive compounds present in ipil-ipil or other agricultural waste as listed or are listed?
For this particular study, we did not do the FTIR analysis for the ipil seeds, so I'm not able to give other specific bioactive compounds as of the moment.
So if you have questions, you can send an email to our to Sir Jolo. So there's a next question. Is there a provision for resorption and reuse of the biosorbents?
At this stage of the research, none yet. Okay. So, but of course, the desorption and then the reuse is also in the future, one of the future goals.
Okay. So are there any more questions? So if you have questions, just type it in the Q&A and Sir Jolo will answer it later on. So if we have no more questions, I think we can proceed to the next parallel session for this PCA colloquium. So thank you very much for having me as your session chair.
Thank you, Ma'am Joy, for moderating our first session. I would also like to thank our first four speakers for sharing their studies. I hope everyone learned a lot from them. So let us now move on to our next session, which is on clean and sustainable extraction technologies. This session will be moderated by Associate Professor Joan Kate Tongpalan. Doc Kate has earned her PhD in University of Queensland, and she has also recently completed her postdoctoral research fellowship in W.H. Bryan Mining and Geology Research Center, Sustainable Minerals Institute in the University of Queensland, Australia. She is involved in various research works in mineral processing and has several publications in international journals. Ladies and gentlemen, Doc Kate.
Hello, thanks so much, Neri, and welcome everyone to our second session. So let's now proceed to our first presenter. Our first speaker is Assistant Professor Carlo Leandro Baladad. Carlo earned his bachelor's and master's degree in metallurgical engineering from the University of the Philippines, Diliman. He took part in a short study program in Hokkaido University and in Akita University in Japan. Currently, he is the program coordinator for metallurgical engineering and has been appointed as the assistant chairperson of the department. So Carlo will give his presentation, High Value Recycling of Silver from Waste Solar Panels Using Concentration and Leaching Methods for the Dr. Meliton U. Ordillas Jr. Professorial Chair in Metallurgical Engineering, sponsored by UP ERDFI member Engineer Mark Villanueva, Met E-Batch 69, who is the owner and CEO of the Whitco Construction and Development Corporation. So, Carlo?
Good afternoon, everyone. First, I would like to thank Engineer Mark Villanueva and his family and Whitco for donating this Professorial Chair Award for Metallurgical Engineering. And to Dr. Meliton Ordillas for continuously inspiring us to do our best. My professorial chair lecture for today is entitled High Value Recycling of Silver from Waste Solar Panels Using Concentration and Leaching Methods. This research was done with my recently graduated advisees, Luis Beltran, Agustin Dominic Laplana, and Mark Francis Tan. We are now living in a world of increasing electronic waste. And that lets us wonder, what are the potential implications? Can anything good come with this? Can any of the components and precious metals like silver be recovered? Today, we will look at potential research on waste solar panels. And you might as well wonder, does every waste solar panel have a silver lining? For this PCA lecture, I will give a brief background of the study and discuss possible research opportunities. An example of waste electrical and electronic equipment are simply known as e-waste, the term used to describe old, end-of-life, or discarded electrical appliances, including discarded computers, consumer electronics, and refrigerators. Here we can see a distribution of the different types of e-waste generated, with small equipment e-waste being the most abundant, followed by large equipment e-waste, which includes solar panel waste. PV waste represent only 0.6% of the annual global e-waste as of 2016. The problems regarding electronic waste aggravate with every passing year of not having any proper treatment and recycling route, especially with the fact that electronic waste is projected to grow each passing year. E-waste recycling routes are personalized depending on the type of electronic waste, and some actually already exist for the more common types of electronic devices such as mobile phones and televisions. However, in the case of solar panels, given that the solar power industry is relatively new, only a few recycling processes on solar panels are established on an industrial scale. There's also limited research on the efficiency of metal recovery processes in waste solar panel recycling. From the International Renewable Energy Agency, the generation of solar panel waste is expected to rise in the coming years. At the end of 2020, the ratio of solar panel waste to installed solar panels is at 5%. However, it is expected to surge to 14% by 2030 and eventually to 80% by 2050. At that point, 5.5 to 6 billion tons of PV panel waste is expected to be generated. This is because countries do not have generally approved solar panel recycling tax, so the waste would continue to accumulate. Additionally, being a composite, these solar panels contain chemicals and components that, when left untreated, eventually get released into the land as toxic substances. Let's put our focus on the growing solar panel industry in the Philippines. Along with other leading countries in solar panel development like China, Japan, Germany, USA, Italy, and India, the Philippines is also steadily expanding its solar market. With several projects in this field, the country is rising to the top in Asia. Philippine facilities occupy 10 slots in Southeast Asia's top 25 solar power plants, and electricity from this technology is expected to triple in 4 years, according to Dutch firm Solar Plaza. Here are examples of projects and solar farms in the Philippines. These solar farms commonly utilize first-generation crystalline silicon panels. As stated earlier, issues will certainly surface in the country in a few years, once these bulk solar panels simultaneously reach their end-of-life phase. Shown here is the composition of first-generation crystalline silicon panels. Most research on crystalline silicon recycling focuses on recovering glass, polymers, and the aluminum. This is because these are the larger compositions by weight. Silver exists as a small percentage on a weight percent basis. Note that silver occurs in the panels as paste to keep the wafers stuck together. However, if we look at the valuation of the different components of the crystalline silicon panels, we can see that silver accounts for the highest material value among the components involved in manufacturing solar panels. Also, we can relate this to the typical grade of an underground ore containing silver, which is around 350 grams per ton if it is high grade, compared to the solar panels, which could reach approximately 1,000 grams of silver per ton. This shows that there is great comparability between solar panels and high-grade silver ores. Thus, waste solar panels can be considered as a potential source for silver. Going further, literature states that the PV industry consumes about 3.5 to 15% of global silver production. Globally, silver is in high demand due to its relative scarcity and rapid usage. Due to this, silver might increase its scarcity, especially as market projections suggest that in 2075, silver production will drastically be reduced. Now, I'd like to go to the next part of my talk, which is to discuss the potential research opportunities on waste solar panels. Research on solar panel waste should be geared towards its high-value recycling, a term used by the European Commission on its Waste Electronic and Electrical Equipment Directive, and as reported by the International Renewable Energy Agency. According to the International Renewable Energy Agency report, the environmental and socio-economic impacts of the different end-of-life waste management options for PV panels have been widely assessed in previous literatures. These assessments have concluded that high-value recycling is the option preferred for all technologies for the benefit of society in general. It not only ensures the recovery of a particular mass percentage of the total panel, but also accounts for minor fractions. The high-value recycling approach is now the foundation for the Waste Electrical and Electronic Equipment Directive, and these should ensure the following. First, the removal and containment of potentially harmful substances such as lead, cadmium, and selenium. The recovery of rare materials such as silver, tellurium, and indium, which should be made available for future use. Materials with high embedded energy value such as glass and silicon will also be recovered. Lastly, recycling processes will consider quality of recovered material. This last part should minimize material losses in what can be considered downcycling operations, wherein materials recovered from PV panels are used for other purposes such as backfill for street construction. The quality of the recovered material should ensure that they can be used again for high-value materials such as the manufacture of more PV panels or electrical and electronic equipment. High-value recycling is a potential research direction that our department can pursue. This talk would mainly focus on the recovery of rare materials, specifically silver. Silver is similar to the metallurgical processes that are applied to ores and minerals. First, there should be a comprehensive characterization, comminution and necessary pre-treatment, potentially a concentration step, and extractive metallurgy processes such as leaching and recovery. The characterization step will serve as the basis of any adjustments in the methodology. At the same time, the results from this step will provide more hints for the optimization part of the study. The pretreatment and sample preparation involves physical and thermal separation techniques. Comminution is the process of breaking down materials into smaller pieces with the purpose of separating the valuable materials from the gangue. Metals from the unwanted components through comminution. It is necessary that they must be separated from the gangue particles. This is achieved through utilizing the inherent physical properties of materials such as density, particle size, and surface properties. Potential concentration methods include gravity concentration to separate light components such as the glass from metal components of the solar panels. Tests can be conducted in the department using our own Falcon gravity concentrator and potentially the shaking or wave table. Flotation of glass can also be a potential process employed. Another interesting study conducted in Hokkaido University is the use of a hybrid jig, which uses gravity concentration and flotation techniques. It is currently being used to separate plastic components of PCBs. Potentially, it can also be applied to crushed solar panel waste. Techniques are also a prominent part of the recovery process of precious metals from solar panel waste. From our review of related literature, several excipient options are available and come with their own advantages and disadvantages. These include traditional excipient options such as nitric acid, cyanide, and aqua regia. Research is also being done using thiosulfate, methanosulfic acid, and the use of halide. This study has chosen to focus, however, on the potential of thiourea as a excipient for silver. It was chosen due to its fast kinetics and low toxicity to the environment. Its main disadvantage is that it is a potential carcinogen in high doses. However, previous studies have shown that only low concentrations are needed, so this risk is significantly minimized. Low recyclability is also a potential issue, which is why research on this process should include ways to solve this issue. This is the main reaction for the dissolution of silver using thiourea. An oxidant ferric sulfate is introduced along with pH adjuster of sulfuric acid to set the pH to between 1 and 2. The reaction needs this level of acidity to proceed. The silver thiourea complex produced will be the solution analyzed for silver recovery using the AAS or ICP-MS. The setup can be conducted using a simple laboratory leaching setup using beakers and a magnetic stirrer. A more ideal setup would be to use a water bath shaker to keep pressure and temperature constant throughout the leaching process. One process option for recovery is precipitation of the silver as silver sulfide by using sodium hydroxide. This is achieved by the reaction of the silver thiourea complex with sulfide ions, causing a displacement which eventually allows the recovery of silver sulfide from the solution. The sulfide ions come from the reaction of excess thiourea in leaching with added sodium hydroxide. The sulfide ions cause the breakdown of the silver thiourea complex since the solubility constant of silver sulfide is around 10 to the negative 51, and solubility in aqueous medium is around 10 to the negative 15 grams per liter. This means the reaction will proceed until all silver from the solution has precipitated into silver sulfide. This leads to the recovery of silver sulfide, which, as stated, has numerous applications. At the same time, precipitation of silver sulfide retains a clean lixiviant as it returns back to the thiourea. This shows how the path chosen allows for lixiviant recyclability, which is a good environmental consideration. Another potential recovery method is through adsorption of the acido-thiourea complex using a bioadsorbent derived from persimmon tannin, as studied by Gurung et al. The research direction could be to find a suitable local source for the tannin bioadsorbent. Another possibility is the use of solvent extraction. A study done by Cho et al. Used trisilophosphin oxide for solvent extraction of silver from nitric acid solutions and used thiourea as a stripping solution. Currently, several samples of waste solar panels have been acquired, which include samples from Canadian Solar, DuPont Apollo, and silicon wafer from Solar Philippines. Future research plans include the continued characterization of the sample, gravity concentration tests using equipment available in the department. Kinetic and optimization tests should also be conducted to master the process of thiourea leaching. Precipitation tests using the previously mentioned reagents should also be conducted. Another option is to search for possible local sources for the preparation of a bioadsorbent. As a conclusion, waste solar panels do have silver linings, and they can be recovered through research. Thank you very much. This is the end of my presentation.
Thank you so much, Carlo, for that presentation. Now we have the floor for questions. Let me just remind everyone that if you have questions, can you just type them in the Q&A box. Are there any questions for Sir Carlo? So I'll just begin. Carlo, this is just to confirm, you haven't done any tests or experiments on these?
Yes po, Doc. Actually, this was supposed to be a undergraduate thesis project, but unfortunately, due to the COVID situation, it was put on hold. So what we have accomplished so far is just uh, the detailed methodology and the comprehensive literature review for the research. But also, as I've mentioned in my lecture, I've also added some other potential research directions that we can pursue in once our operations normalize. And this can be additional projects for students or for researchers in the department.
Okay. There's a question from Sir Tito. I think this is a related question to what you have already answered. But he said,
Yeah.
thanks, Carlo. Now that you have crafted the research plan, how do we move forward?
Actually, I'm our my through my advices and through the some local governments, we have already received some uh, financial support to get things started. So we will work using that to gather initial data. But I'm also looking uh, to submit proposals within UP, especially through the OVCRD, to the outside research grants, and eventually, if we have gathered enough data, we might also want to pursue proposing a project through the DOST through so that we can have a bigger budget to actually produce a working pilot of the technology if ever the laboratory scale tests would be successful.
Okay. Have you contacted any company
Um,
who could be your
so far
potential
in
sponsors?
So far, what we have, the companies that we've contacted are the companies that we asked the solar waste panels from. So we have obtained solar panel waste from certain companies, but we're also looking to propose to major companies because one of the requirements now of DOST through their I think their Cradle project is to have a private company sponsor or private company component of the project.
Yeah.
So that's one of the directions we're looking at. Uh, and I think it would be beneficial for companies to have this kind of technology so that they can save on the manufacture of their solar panels.
Yeah. There's a follow-up question from Sir Tito again. What is the reaction of the panel manufacturers? When you have contacted them, are they very much willing to support?
Actually, as for that, Sir Tito, we haven't really shown them the exact technology or basically what we plan to do. All we've done is really ask for their waste solar panel so that we can pursue research. But eventually, we would like to give a more detailed proposal to them so that they can look at the technology and determine if it's really beneficial for them. But for the near future, we'll build that proposal so that we can have a good presentation to our target company.
Okay. There's another question here. Is this an opportunity to patent any part of the methodology once proven in practice?
I think so. There are many opportunities to create a patent, especially for the process application to solar panels because from our research, most of the research being done on diarrhea leaching applies to uh, recovery of metals from PCBs or other electronic waste. So only limited research has been done for actual solar waste recycling. So and also if we can find maybe a local adsorbent, since one of the process options is to have a bioadsorbent to recover the acidothiorea complex. So I guess if we combine that with the leaching process using thiorea and create a design for a pilot plant, eventually we can apply for a patent.
Okay. Yeah, great. All right. Another question. You mentioned that there are existing industrial processing plants in other countries that are recycling valuable components of PV panels. Do you have idea why they have not recovered silver yet, despite the fact that it is the most high value component?
I think most of the industrialized companies in other countries does not really focus yet on the specific recovery of solar panel waste. Most of the industrial companies recovering precious metals from e-waste recover waste metals from more popular devices like cellular phones, appliances, even the recycling companies that I've visited in Japan process these kinds of waste. They also process appliances like refrigerators, televisions. So I don't think there's now a big company that only focuses on recycling this solar waste panel.
Right, thank you. There's another question from Stan. Carlo, do you have any idea on the expected percent yield of this leaching process?
For the diarrhea leaching, based on from previous studies, but again, these research studies are used on waste PCBs. But when using diarrhea as an excipient, it can reach up to 90% extraction at around 2 hours of leaching. So we're all hoping to further optimize that as it applies to waste solar panels.
Okay. This one is not a question, but it's a comment from Sir Tito. Please prepare the proposal, Carlo. The 100 grams per ton is very interesting compared to 350 grams per ton from high-grade ore. But I have a question regarding that. Do you think in terms of processing or recovering silver from the primary source is comparable also when you recover it from secondary source, such as from the solar panels or e-waste?
Definitely in terms of recovery of precious metals, recovery from secondary waste can never replace the recovery from primary sources. So of course, the primary sources would still be the most economical one to recover. But the metal recovered from secondary sources can supplement the supply coming from the ore. So, and also just to create additional value to materials that are supposed to go to waste. But I think, in my opinion, it can never replace primary sources. But yes, just also to react to Dr. Tito, definitely we're gonna be working on a proposal that we can forward to either UP or to the OSP.
Okay. Thank you. Is there any other question for Carlo? If you have question later on that you can think of, just type in here and probably Carlo can answer you, or you can always email him as well. So thank you so much, Carlo, for that presentation. Let's now proceed to the second presenter.
Thank you.
Our second speaker is Assistant Professor Joy Marisol Manyao. She'll be presenting her research on the effect of banana-based enzyme on the cyanidation of sulfidic gold-bearing ore for the SR Metals Professorial Chair. So Joy graduated cum laude with a bachelor's degree and also obtained her master's degree in metallurgical engineering from the University of the Philippines. She is the faculty in charge of the metallurgical pilot plant and the student affairs and Tambayan committee head of the department. Her research interests include metal recovery, electrometallurgy, and mineral processing. So let's give it a go, Joy.
Good afternoon, everyone. It is my pleasure to present in this afternoon's PCA Colloquium our study entitled Effect of Banana-Based Enzyme on the Leaching of Sulfidic Gold Ore. This study is in partnership with my previously undergraduate advisees, Ms. Danica Michelle Ibiacora and Mr. Vince Albert Ibn Biahe. Gold is one of the most useful metals due to its desirable properties. Due to its good physical and chemical characteristics, it is widely used in different industries. Gold is one of the major commodities that we have here in the Philippines, and we have different mining industries with gold as their main product. The processing of gold ores is based on its mineralogical composition, concentration, and the nature of the minerals. We see here that the gold-bearing materials can be classified as primary ores or secondary materials. The primary ores can be further classified into free milling or refractory gold ores, which is normally processed here in the country. The free milling ores are those where greater than 90% of the gold can be recovered through conventional cyanide leaching. The reason for here is the gold occurs as your readily liberated material. On the other hand, refractory gold ores are those that give low recoveries and need more complex and rigorous process. The most widely used hydrometallurgical process for gold is still cyanidation. For the cyanidation process, the gold reacts with your cyanide and your oxygen to form your gold cyanide complex. The issue, however, with your cyanide is the level of hazard of the reagents used. Proper precaution should be taken care when using your cyanide. Another issue with your cyanidation process is that your refractory gold ores cannot be simply leached with simple cyanidation alone. This is because the presence of sulfides in your gold ores could either increase or decrease your oxygen and your cyanide consumption. The reason is cyanide is an aggressive compound wherein it has a high tendency to react with the other constituent materials in your refractory gold ores. So the presence of sulfides, especially in your refractory gold ores, limits the capability of cyanidation into the leaching of gold. The reason is, as we mentioned earlier, the presence of oxygen-consuming minerals such as your pyrrhotite, marcasite, and arsenopyrite, and your cyanide-consuming minerals such as your arsenopyrite, copper, pyrite, bornite, stibnite, and galena. Both hydrometallurgical and pyrometallurgical processes of oxidation were developed in order to solve the issue of sulfide presence in gold ore being processed. However, the usage of such pre-treatment operations impose economic process constraints. There are several studies conducted which aims to solve the problem of sulfide presence in cyanidation consumption, which includes the introduction of alternative lixiviants, addition of catalysts, and innovative replacement to the leaching circuits of gold ores. Aside from gearing towards more efficient parameters in metallurgical processes, modern metallurgy techniques are being used to continue exploring for viable process. One process which is being introduced is the addition of enzymes in your leaching operations. This is one of the promising yet to be explored techniques that could significantly improve the recoveries of your base metal. So one particular reaction is the conversion of insoluble copper sulfide into copper 2+. In order for the reaction to move forward, a continuous addition of Fe3+ is needed for the conversion of your sulfide to your copper 2+ ions. A patent filed by Rox and Chaiko made use of a bacterial enzyme, rusticyanine, with an addition of a detergent polymer for stabilization in order to recycle the Fe ions produced in the product side so that it can be converted into your Fe3+ to the reactant side. By doing so, the forward reaction is favored. An additional study which made use of the enzyme is a study by Santiago and Vergara, which are previous students from the department, wherein they studied the effect of banana-based enzyme on the cyanidation of non-sulfidic gold-bearing ore. So for this study, they used a commercial-based enzyme wherein it has 98% banana skin and 2% NaOH. So this was the same enzyme that would be used in this study. And they observed that there's an increase in percent recovery and cyanide consumption by the addition of the enzyme. So this study is one of the motivation in doing this research. So focusing on the sulfidic gold ore. So why banana peel? Banana peel contains enzymes such as oxalate oxidase and superoxide dimutase. So we see here the reaction of both of the enzymes, wherein we see the reaction mechanism showing the oxidation of your oxalate, forming your carbon dioxide and hydrogen peroxide. On the other hand, the catalysis of your superoxide dismutase shows the reaction with your H plus ions to form your oxygen and your hydrogen peroxide. So with all of this information, this particular study aims to investigate the effect of adding banana-based enzyme on the overall gold dissolution in the cyanidation of sulfidic gold-bearing ore. In order to achieve this, the methodology would comprise of ore and enzyme characterization, gold dissolution run, and a simple statistical analysis. So for the ore characterization, XRD and XRF was used to determine the minerals present in the ore samples. And from the XRD analysis with the use of match software, it was found that significant amount of quartz and presence of sulfides such as bornite, collucite, sphalerite, tetrahedrite, and pyrite were found. To check the elemental composition, XRF was used for both the solid and acid digested sample. And we see here 5.3 ppm or 7.2 ppm of your gold. And the result of the XRF wherein you have the different base metals and other minerals coincides with the result from your XRD analysis. And the result here also coincides with the result provided by the mining company which gave the ore, which is Lepanto Mining Consolidated Mineral. So from the result here, it's still not enough to state that the ore provided is refractory ore because this can only be proved by the cyanidation process. So we'll look into that later on. So another ore characterization used is the mesh of grind study, which is used to determine the time needed to produce an approximately uniform particle size. So for this case, we use the result provided by the mining company where it states that the liberation size is minus 230 mesh. So for the performed experiment, the time needed is 33 minutes and 45 seconds with a confirmatory run producing 82.91% passing 230 mesh. So we see a slight difference of 2.91% from the target 80%. So it's important to maintain this particle size because this is the estimated liberation size of the mineral wherein enhanced recovery is achieved at particle sizes near the liberation size of the target mineral. So on the other hand, for the enzyme, FTIR was used to characterize the enzyme and determine the functional groups available. So from the FTIR result, we found out that there are 3 functional groups present and 4 possible enzymes. So you have B-amylase of the hydroxyl group, acrylamide of the imine group, catechol oxidase of the carbonyl group, and isopentyl acetate also of the carbonyl group. So your hydroxyl group or your hydroxyl is an entity with a formula of OH meaning it contains oxygen bonded to your hydrogen. An imine or imine group contain carbon-nitrogen double bond, wherein your nitrogen can be attached to your hydrogen or an organic group. On the other hand, a carbonyl group is a functional group composed of your carbon atom double bonded to an oxygen atom. So we see that for all the three groups, it's oxygen rich, but the information that we have is not enough for us to determine the mechanism on how the functional groups present in the enzyme will affect the recovery. So moving forward to the gold dissolution run, so bottle roll testing was used to analyze the effect of adding enzyme. Cyanide strength, particle size, percent solid, enzyme dosage, and pH were kept constant, but it's varied based on the type of run, wherein you have cyanide and enzyme run, cyanide only run, and enzyme only run. So for the results, the addition of enzyme showed an improved recovery of up to 6% gold, wherein the maximum recovery for the particular run use is approximately 13.43% recovery. So we see here a low amount of gold recovery, especially for the cyanide only run, which further correlates our hypothesis that the ore provided is a type of refractory gold ore, since it has low recovery at the specific cyanide concentration. It's interesting to see that the addition of enzyme alone actually shows approximately 5% gold recovery. And we see that the addition of enzyme for both the enzyme only run and the cyanide plus enzyme run shows an improvement in the percent recovery of gold. So aside from the recovery, the cyanide consumption was also monitored. And from the result, we have trial 1 and trial 2 for the cyanide only run, then trial 1 and trial 2 for the cyanide plus enzyme run. For this particular result, we see a consistency of cyanide consumption for the cyanide plus enzyme run. This provides us better and accurate observation on the gold recovery. And to further analyze this, we computed for the cyanide equivalent of the recovered gold from the dissolution test. So from the result, we see a higher amount of cyanide consumed for your cyanide plus enzyme run, meaning that one possible mechanism is that the addition of the enzyme improves the usage of your free cyanide for the dissolution of gold. Another interesting result here is that we see that even if you have higher cyanide consumption for the cyanide plus enzyme run, the percent consumed by your cyanosides or your other cyanide forming complex minerals is the same for both. So we appreciate the addition of enzyme in our gold dissolution run. Aside from the 3 runs, the enzyme dosage was also studied in this experiment, wherein it's varied at 2%, 4%, and 6%. And we see a higher recovery at higher concentration of enzyme at fixed cyanide dosage with 30.89% highest recovery at 6% volume per volume enzyme. So we see a significant increase in the percent recovery of gold when we increase the amount of enzyme added into the solution. To further confirm this, a one-way analysis of variance was conducted at 90% confidence interval, and it shows that the enzyme dosage has a significant effect on the gold dissolution. So this is the summary of the ANOVA calculations at 90% confidence level. So in summary, the addition of enzyme was found to be positive as it increases the percent recovery of gold. And we observe the improvement of percent recovery by increasing dosage of the enzyme. It also increases the cyanide consumption, which can be seen as a drawback if we want to reduce the amount of cyanide. this is further to be studied, but we observe that enzyme alone can reach the gold ore. So some recommendations for this study is better process control, more sample runs, multiple enzyme dosages runs in particular, and optimization studies, kinetic modeling for the determination of the rate determining step for better improvement of the dissolution process, and an in-depth study of the effect of enzyme on the mechanism of the reaction. So here are the references used for this study. And thank you for listening. And I would like to thank the SR Metals for this professorial chair award.
Thank you so much, Joy. That was an interesting presentation. So we are now open for questions for Joy. So just type in your question on the Q&A box. Right, here it is. What variety of banana is being used?
The banana-based enzyme used is actually a commercially based enzyme. So we have actually no idea where it come from. So one of the reasons why I did not mention where we got the enzyme is due to privacy reason. So I can't answer the specific variety of the banana species used for this particular study. But from the references that we have seen, most of the banana peel based enzyme has the two oxidase and dismutase component.
Okay, so that means then that we cannot just use any banana, right?
Yes.
It would have been good if we can use any to reduce our waste. Anyway, there's
Yes,
another question here. Roughly how many tons of banana peel do you need to process 1 ton of gold ore?
For this particular question, since the group was not able to actually extract the enzyme from the banana peel, so I can't estimate the amount of banana that can be used. But from the enzyme that the commercially available enzyme, so the sample run is approximately 100 to 200 grams of the ore, and we use around 2 to 10 ml of the provided enzyme.
Okay. Another question. Would the maturity or ripeness of banana have an effect on the quality or quantity of enzyme?
I do not have a specialty on this particular question, but I think from references or literature, the ripeness of your material actually affects the enzyme present in your material. So there's a possibility that the maturity and ripeness can also affect the quantity of or the quality of the enzymes, the quality or quantity of the enzyme that can be produced.
Okay. So it would then be if you are planning to have if you have future plans,
Follow up, yes.
it would be good to characterize also the enzyme and look at if just any banana could be used, or just characterize the banana. Yeah. Do you have other questions? I just want to confirm, because in your plot of the recovery, is that percentage recovery?
Yes, Doc. It's percentage recovery. So we
Yeah,
actually have, yes, po.
Yep, go ahead.
We actually have very low recoveries for all the runs, which supports the idea that the material provided is a sulfidic ore. So from the percent recovery, it's not as high as you would expect, but we see an increase in the percent recovery. So So as high as 30% when we adjusted the dosage of the enzyme, but it's still very low if you would compare it to pre-treatment oxidation wherein you would be using roasting and other hydrometallurgical processes. So it's a little bit low since we did not
Yeah.
perform too much of
Yeah.
optimization runs or other substitute runs. But we see an improve in the percent recovery.
Yeah, because that's actually one of my comments, because I've noticed the recovery is just 11 to
Yes po.
13%. And then the other one is just 30%, which is not just slightly low, but it's very low.
Very low as opposed
Yeah.
to your pre-oxidation,
Yeah. Yeah.
typical pre-oxidation processes.
Yeah. Probably with more optimization tests, we could really increase the recovery. All right, here we go. There are other questions here. Are enzyme-assisted extractions common in the industry?
So far, the enzymes that are normally used in the industry are enzymes produced by your bacterial processing. So, like I've mentioned earlier, but for plant-based, so when we are actually looking for reference, there are very few, but there are increasing usage of plant-based lixiviants or plant-based additives for the improvement of the recovery of your base metals. So this is based on our literature before, but there are actually very few who uses the technology.
Yeah, okay. I think this is a follow-up question from my question a while ago. Why do you think it has a low recovery?
From the cyanidation alone, the recovery is actually very low. This means that you have a high amount of sulfide present. And one reason that I haven't mentioned is the cyanide dosage that we have added for the leaching operation is not as high as those usually used in the industry, because for this particular study, we based it on a previously conducted experiment, and we have yet to study the interaction of the cyanide dosage and the enzyme dosage in order to see improvement in the recovery process.
Yeah. Yeah. I was just about to suggest also for your future plan that to have a mineralogical analysis or mineralogical measurement on the ore, so that you can really investigate the occurrence of the gold.
Of the gold.
Yeah. All right. Another question is that, do you think this is cost effective, like using the banana-based enzyme? And related to that one is, do you think that the addition of the enzyme will have an effect on the subsequent recovery process using activated carbon?
Okay,
So
so
will it be effective also with activated carbon?
for the first question, I think I don't have the right resources to answer if it would be cost effective. But if you improve the process by using banana-based enzyme, then definitely it would be cost effective. But it's too early to tell if the process is cost effective, because uh, it's just this research is just more of a proof of concept that it actually improves the recovery. So I can't answer if the process would be cost effective. But if it becomes successful, then it can be, because for this case, you are reducing the addition of your pre-oxidation processes, which is normally your roasting process, the addition of other steps in order to improve the recovery of your refractory gold ore. For the next question, do you think that the addition of enzyme will have an effect on the recovery? Uh, we haven't studied this, but if if cyanide alone is the main component reacting with your gold, then there's a possibility that it cannot affect. But if we recall, for your adsorption process, you have to decrease the amount of oxygen. if you would recall your reaction. So there's a possibility that it can affect in that way, since from the FTIR results, we see that your banana-based enzyme has oxygen, it's a very oxygen rich functional group. So there's a possibility that it can affect on the recovery in terms of the oxygen. For the other components present in the banana base enzyme that we have not studied, so I'm not sure if those will interfere in the carbon absorption process of your gold.
Thank you very much, Mom Joy. I think Doc Kate has been disconnected. Ayan, there she is po.
Hello, Doc. Doc, ano po? We can't hear you. We can hear you po, Doc. Medyo mahina.
Let us give Doc Kate to transfer, time to transfer po muna. Saglit lang po. We are having technical difficulties.
Wait lang. Wait lang.
Hello, I'm back. Sorry for that technical difficulty. Now I am using Assistant Professor Carlos' account because I cannot log into the Wi-Fi. Anyways, all right. So for our third speaker, we have Assistant Professor Terence Lucero Menor, and he will be giving his presentation entitled "Leaching Behavior of Iron, Nickel, Chromium, and Manganese from Geotitic Laterite in Sulfuric Acid" for the Willie Lim Bontek Engineering Mining Centennial Professorial Chair. So Terence earned his bachelor's and master's degree in metallurgical engineering from the University of the Philippines, Diliman, and joined the faculty afterwards. His research work focuses on hydrometallurgical extraction of precious and base metals from primary and secondary resources, kinetics of metallurgical reactions, and surface science. So, Terence.
Magandang hapon sa inyong lahat. I am Terence Minor and I will be presenting my study on the leaching behavior of iron, nickel, chromium, and manganese from goethitic laterite and sulfuric acid for the Willie Lim Bontek Mining Engineering Centennial Professorial Chair Award. As an overview of this presentation, I will be providing you some details on the laterite deposit and atmospheric leaching, followed by the results of leaching experiments and response surface methodology, and lastly, the observed correlation between the metal recoveries that can be attributed to the structure of the laterite. Most nickel production is used in alloying elements with around 58% for the manufacture of stainless steel and 23% for other alloys. Other applications include plating, which is 9%, and batteries, 5%. In the recent years, there have been an increase in the demand for nickel, primarily driven by the electric vehicle markets as raw material for battery production. Nickel can be mined from two ore types, sulfide or laterite. Despite the abundance of laterites with an estimate of 72% of the world land-based nickel resources, only 42% of the world's nickel production is from laterites. The preference for sulfide processing can be attributed to the complex processing involved in recovering nickel from laterite ores. However, the depleting sulfide resources and increase in demand in nickel have resulted into shift towards laterite processing for nickel production. The Philippines is blessed with abundant nickel laterite deposit, having 17% of the world's nickel laterite deposit. Recent studies have been focusing on leaching of laterite at atmospheric conditions, which is much cheaper than the widely used and most effective high-pressure acid leaching process. However, key issues in atmospheric leaching is the kinetics of extraction and the significant presence of other metal ions in the leach liquor. As the electric vehicle demand requires nickel of considerable purity, accounting of impurities is necessary in order to determine the subsequent process for purification. With this, the study aims to investigate the leaching behavior of laterite ore in sulfuric acid media at atmospheric pressure. Specifically, this study aims to determine the effect of time and temperature on the leaching behavior of laterite and compare the recoveries of iron, nickel, chromium, and manganese. Leaching experiments were performed in two neck flasks fitted with a Graham condenser and temperature probe. The condenser is connected to a pump submerged in water below room temperature. 4 molars of H2SO4 was added to the flask and heated in an oil bath at the desired temperature. Laterite was then added at a solid loading of 20% by weight. The mixture were mechanically stirred at 500 RPM. After the specified reaction time, the solutions were quenched in water at room temperature. The solid was then filtered and the pregnant solution was stored in plastic vials. The pregnant solution obtained were analyzed using XRF analyzer. Acid digestion of the laterite ore sample was also performed. The solution was analyzed for chemical composition using XRF analyzer. XRD analysis for the laterite was also performed. Factors investigated were time, ranging from 2.75 to 11.25 hours, and temperature ranging from 30 to 88.6 degrees Celsius. Response variables are the leaching recoveries of iron, nickel, chromium, and manganese calculated from the measured composition of these metals in the leach solutions. Central composite design was used with the following treatment combinations. This figure shows the XRD pattern of the laterite. The pattern was analyzed using crystal impacts match, a face identification software. The face identification showed that the laterite ore is composed mainly of goethite. XRF analysis of the digested sample shows that the sample is mainly composed of iron, which is expected, and nickel, chromium, and manganese concentrations of less than 1%. This table shows the recoveries obtained from the treatment combinations. Recoveries obtained for iron, nickel, chromium, and manganese at 80 degrees Celsius and 10 hours are 49.8%, 46.1%, 33.2%, and 62.7% respectively. In order to show the leaching behavior of the metals, models were fitted in the obtained results. This was done using StatEase's design expert. Using lack of fit tests and adjusted R-squared values, it was determined that iron, nickel, and chromium recoveries follow a linear model, while manganese follows a quadratic model. Analysis of variance for the response surface models showed that for iron, nickel, and chromium, main factor effects are significant. For manganese, main factor effects and B squared are significant. Insignificant model terms were then removed from the model and contour plots of the models for each response variable was then obtained. As shown in these contour plots, increasing the time and temperature results to an increase in the recovery for all the 4 metals, with temperature being the most significant. This is expected as the kinetics of leaching of goethite is improved at higher temperatures. Reaction time was also expected to have a positive effect on recovery as increasing contact time results to higher metal dissolution. However, it was also observed that extending the reaction time from 10 hours to 24 hours at 80 degrees Celsius have no significant effect on the recovery, which is maintained at around 50% for iron and nickel. This is attributed to the consumption of the acid content of the leaching solution after 10 hours. Titration revealed that acid concentration dropped to below 0.2 molarity. From these contour plots, it is apparent that the recovery rate of iron, nickel, chromium, and manganese appear to be correlated. To further clarify the correlation, the recoveries obtained for nickel, chromium, and manganese were plotted against the recovery of iron. Interestingly, nickel iron and chromium iron plots has an R-squared value of almost 1, while manganese iron plot has an R-squared value of 0.962, indicating significant correlation between the recoveries. The observed correlation can be attributed to the isomorphous substitution of nickel 2+, Cr3+, and Mn3+, for Fe3+ in the goethite structure. Singh et al. Observed that the isomorphous substitution by the three transition metals in synthesized goethite is up to 5 mole%, 8 mole%, and 15 mole% respectively. They also noted that there is no evidence for separate nickel, chromium, and manganese hydroxide phases. Slope of almost 1 for nickel Fe recovery plot may indicate uniform isomorphic substitution of nickel in the goethite structure. Cr and Mn may be incorporated in other phases in the laterite, though this requires further mineralogical analysis to verify. This work demonstrated that increase in time and temperature results to increase in recoveries of iron, nickel, chromium, and manganese. Linear correlation on recoveries of metals was observed, which is attributed to isomorphic substitution of nickel 2+, Cr3+, and Mn3+, for Fe3+ in the goethite structure. This means that selective leaching of nickel from goethitic laterite in atmospheric pressure is difficult. Thus, to dissolve nickel, the goethite must be completely dissolved. As a result, acid consumption will be high. For future work, as mentioned earlier, further mineralogical and geochemical analysis on laterite ore is needed in order to identify the form of nickel and other metals in the laterite sample, whether these metals are completely substituted in the goethite structure or in other existing phases in the ore. Also, because of equipment limitations, the leaching behavior of aluminum was not covered. This may also be investigated in the future. The metals investigated in this study are those with the highest concentrations in the leach solution. The amount of these impurities must be considered in the subsequent processes. Before I end this presentation, I would like to thank my undergraduate advisors, Castle and Balds. Their thesis topic compelled me to work on this study. They wanted to produce nickel sulfate from laterite and were supposed to use these results as one of the bases for their methodology. Unfortunately, they were not able to fully execute their thesis because of the pandemic. To Mambing, some of the compositional analysis were performed by her class, and of course to April for her support. Maraming salamat sa inyong pakikinig.
Maraming salamat din, Terence. And we would also like to thank the donor for the Willie Lim Bontech Mining Engineering Centennial Professorial Chair, brothers Dr. Henry Lim Bon Leong, ME Batch 73, and also ERDFI member, Joseph Lim Bon Juan and Jerry Lim Bon Hyong of the Lim Family's Sterling Paper Products Group. Thanks, Terence. So now we are now open for questions. So if you have questions for Terence, just type in the Q&A box. So Terence, do you think that your method would be comparable to HPAL? Terence, we can't hear you.
Sound check.
Oh, there you go.
Okay
Yeah.
na po, Doc.
Okay na. Oo.
Ayun. So actually no, kasi in HPAL, co-precipitation of iron or iron occurs during the leaching process, resulting into high purity nickel and cobalt solutions. In ano po, in atmospheric leaching, yun, iron stays in the leach solution. And then aside from that, the hydrolysis of iron in HPAL results into further production of acid which assists in the dissolution of nickel from the laterite ore. So therefore, HPAL is more efficient. However, atmospheric leaching is much cheaper.
Yeah. Okay. But will there be a potential that although it won't be as maybe as efficient or as effective as HPAL, do you think that there's somehow a potential if you just optimize or, you know, revise or add something in the method?
Actually, there is, Doc, kasi the basis of also of the methodology proposed by my students was on a patent made in China. So the patent actually do two-stage atmospheric leaching process. So after the H2SO4 leaching, precipitation of the impurities is done using carbonate and then another leaching to get the nickel from the precipitates. So it is possible. It is already done in China. Though I think there can be other options to explore for the processing of nickel. Other processes, I mean.
Yeah, great. Thanks, Terence. Right. Which companies should we convince? This is from Sir Tito. Should we convince to support further research work?
Actually, yes po kasi there is limited extractive industries on nickel in the country. So if we further explore the extraction processes for nickel, I think some of the companies in the Philippines may apply those processes.
Okay. From Jason Pinza he said, sorry, I might have missed it, but where did you get the samples?
I am not yet sure if I am allowed to tell where I got
That's
the
all right.
sample. Yes,
Yeah.
but it's just obtained locally. It's obtained from the Philippines.
It's from Philippines. Yeah, that's right. Great. Any other question for Terence? Okay, Jason asked again, did you do multiple regression analyses?
The response surface methodology showed that linear model is the best fit for the recovery. So yes, the response surface model is
Okay. I think what he wanted to ask is that the ions themselves might have effect on their substitution on the structure. Do you think that the ions might have an effect on the substitution?
actually based on studies, there is a uniform substitution of of the ions considered in the goldfitic structure, and then these ions exist as other phases when they reach the maximum mole percent.
Okay. Right. From Sir Algen Sekila, at what degree of temperature we can have optimum recovery?
Since this is atmospheric pressure leaching, we limited it to 80 degrees Celsius. Beyond that temperature, there is the boiling affects the reaction. So there is, what do you call that? Basta masyadong mataas po yung, matindi yung boiling. So, yun, hindi okay yung nagiging leaching.
Okay. A follow-up question from Sir Tito. I thought there are 18 companies doing nickel ore extraction as we supply 72% of the world's nickel ore supply.
Most of the processing is on production of sulfides, the major processing plants. do production of sulfides and export it for further processing in other countries. And then there is no, I'm not sure if there are existing small companies, though yun, most of the large companies only focus on another raw material for nickel. And then the purpose of this study is to focus more on production of nickel sulfate, which is different from the production of metallic nickel. And then there is no, of course, nickel sulfate production in the Philippines.
Okay, thanks, Terence. Do we have other questions for Terence? Okay, if there is none, then that's it for the second session. Again, thank you so much to all our speakers. And also, of course, we'd like to thank all the donors for the professorial chairs. And thank you. And that's all for the second session.
Thank you very much, Doc Kate, for moderating our second session. And thank you to our speakers. I hope everyone gained a lot from the Clean and Sustainable Extraction Technology session. Let us now move forward to our third and last session this afternoon. So our third session is on enabling technologies in materials. This will be moderated by Mr. Miguel Lloro, a university researcher too from the Materials R&D and Consulting Facility of the department. Miguel?
Hi, Neri. Thank you for that. So for first speaker, Dr. Eden May de la Peña earned her PhD from the University of Strathclyde in Scotland, UK, with a degree in Chemical and Process Engineering, Materials track. She is currently a tenured faculty in the department, and she established the Sustainable Electrochemical Technologies Laboratory, where she currently leads 4 fully funded research projects. She is also currently serving as the Associate Dean for Public Service of the UP College of Engineering, as well as the President of the Institute of Materials Engineering of the Philippines. Dr. de la Peña is a strong advocate of women empowerment in STEM, where she regularly gives talks to the Women Empowerment STEM series. This platform aims to inspire high school girls to take up courses in science and engineering. For this award, we would like to recognize the contribution of Dr. Antonio Tanchuling Jr. Everyone, let us welcome Dr. de la Peña with her presentation for the Antonio and Lourdes Tanchuling Mining Engineering Centennial Professorial Chair Award.
A pleasant afternoon, everyone. Let me share with you my research on the electropolishing of aluminum using choline chloride-based solvent. I am Eden May de la Peña, and this presentation is for the Antonio and Lourdes Tanchuling Mining Engineering Centennial Professorial Chair Award.
Aluminum is an important technological metal due to its strength, lightweight property, corrosion resistance, non-toxicity, ductility, and malleability. These properties allow aluminum to exhibit a high degree of stability, long service lifetime, good machinability, and excellent formability. Electropolishing is considered one of the most popular approach in imparting a highly polished surface to aluminum. Electropolishing is the controlled dissolution of a metal surface by the passage of electric current at a particular potential in an electrolytic medium. Electropolishing traditionally uses strong concentrated acids. Several problems arise from the use of these corrosive liquids. One example is extensive gassing. Additionally, since electropolishing is performed at high temperatures, then electrolytes are rendered more aggressive. These chemicals not only pose a serious threat to process infrastructures, but more seriously, endanger humans and harms the environment. Hence, future studies are geared towards looking for alternative technologies that could do aluminum polishing using cost-effective, non-toxic, and biodegradable electrolytes. One promising approach is the use of a novel and unique material called ionic liquids. Ionic liquids consist primarily of salts in liquid form. Due to their unique properties, Ionic liquids have found use in different applications, including gas and wastewater treatment, energy, and surface modification processes such as electroplating, electroless plating, and electropolishing. Deep eutectic solvents, or DES, is a type of ionic liquids that has recently gained research interest, particularly as an electrolyte that could replace traditional aqueous solution for electrochemical processes. Some of the advantages of using DES in electrochemical processes include wide potential window, high solubility of metal salts, avoidance of water-metal chemistry, and high conductivity. One of the most critical advantages of DES is that it is non-toxic and biodegradable. This implies that DES offer a truly clean and green alternative to the traditional electrolytes that consist of environmentally harmful aqueous solutions. Thus, in this study, we want to look at the feasibility of using DES ethylene for aluminum electropolishing. There were 4 phases in this research: the ethylene synthesis, electrochemical evaluation, electropolishing experiments, ethylene chloride to ethylene glycol in a 1:2 molar ratio mixture. The mixture was heated at 70 to 80 degrees Celsius and constantly stirred until a colorless and homogeneous solution was obtained. The synthesized solvent was allowed to cool to room temperature and stored in a tightly sealed glass container to prevent moisture absorption. Linear sweep voltammetry, or LSV, was performed using a potentiostat and a 3-electrode apparatus as shown in this picture. The 3-electrode apparatus consists of aluminum as the working electrode, stainless steel as the counter electrode, and platinum as the pseudo-reference electrode. The electrodes were attached to the potentiostat and the voltammetry test was initialized using the NOVA 2.1 software. LSV was done in potentiostatic mode at a potential range of 0 to 5 volts and a scan rate of 20 millivolts per second. Electropolishing of aluminum was conducted following the settings for the applied voltage and time as shown in this table. The applied voltage was based on the results of LSV analysis. The 3 regions characteristic of electropolishing systems in aqueous solutions were observed in the ethylene system, namely the etching region from 0 to 2.7 volts, the passivation region from 2.7 to 4 volts, and polishing region from 4 to 5 volts. The maximum current density, which occurs at the peak between the etching and passivation region, was 16.9 milliamps per centimeter squared, while the limiting current density of the polishing process was 12 milliamps per centimeter squared. More importantly, the existence of the polishing region, or region 3, in the polarization curve indicates the possibility of conducting aluminum electropolishing in ethylene. This figure shows the metallurgical microscope images of the unpolished aluminum, alongside micrographs for the specimens electropolished at different conditions. The surface of the unpolished aluminum exhibited scratch marks brought about by mechanical grinding. For the specimens polished at 4.3 volts, a change in the surface quality was observed. Initial visual inspection indicates some improvement in surface shine or glossiness. A closer look at the surface revealed that the scratches from the previous surface preparation step was removed and replaced by smooth nodular features at the surface. The diameter of the nodules ranges from 20 to 80 microns. At this point, we can say that with increasing polishing time, the nodules become more prominent and well-defined. This observation confirms the electropolishing is indeed feasible at 4.3 volts as predicted by the LSB curve. For the specimens polished at 6 volts, the features came out differently compared to those seen in the specimens polished at the lower potential, which is 4.3 volts. At 15 minutes electropolishing time, the surface appears amorphous with no definite features standing out. At 25 minutes, light scratches were made visible, and at 35 minutes, the surface appeared polished and the same nodular structure that was previously seen in the specimens polished at 4.3 volts can be observed. Results indicate that only the aluminum electropolished at 6 volts for 35 minutes exhibited a polishing effect. For the 15 and 25 minutes, although they possessed surface features different from the control, did not exhibit polished surface characterized by the presence of smooth grains. It is possible that only passivation instead of material dissolution occurred for these specimens. These figures present the SEM images of the unpolished specimen and the aluminum specimens electropolished at 4.3 for 35 minutes and 6 volts for 35 minutes. In the control, only scratches from the previous surface preparation treatment are visible. In contrast, the two electropolished specimens possess very similar morphology containing the nodular or hemispherical surface features. The 4.3 volts appeared to have more defined structure than 6 volts. AFM analysis was conducted to gather quantitative information of the specimen's surface roughness. This figure shows the results of AFM imaging of the control or the unpolished specimen. The surface exhibited alternating parallel ridge-like structures. This feature likely relates to the surface scratches created by the initial mechanical grinding. While these figures present the AFM images of the aluminum electropolish at different settings, remnants of the ridge-like features seen in the control are still evident in these specimens. However, the surface appears relatively smoothened and the presence of hemispherical protrusions are also noticeable, which agrees with the nodular features observed under the SEM. This is the plot of the average roughness, or RA, versus electropolishing time for the specimens polished at 6 and 4.3 volts. It can be observed that the lowest surface roughness is obtained at 25 minutes for 4.3 volts and 15 minutes for 6 volts. In both voltage settings, increasing the processing time decreases the roughness until achieving the optimum electropolishing time. Beyond the optimum time, RA increases. It is likely that the mechanism that produced the observed nodular features in the electropolished aluminum is a product of the interaction between the ionic liquid molecule and the double-layer structure produced at the interface. As of yet, the interaction is not yet well understood, though several models have been proposed. The hemispherical shape suggests localized, non-uniform polishing or etching rate, that is, the perimeter of the hemisphere has been etched faster than its middle. This would mean that certain areas bear enhanced electric fields that encourages faster metal dissolution. Additional studies are necessary to understand this mechanism further. Future research may look at the electrical double-layer characteristics as a function of electrolyte composition and the influence of surface preparation on the substrate. There is a possibility that these nodules actually outline aluminum grains and grain boundaries, and it is recommended that future work may also consider this prospect. Here are our takeaways from this study. The electrochemical polishing of aluminum was successfully conducted using ethylene. After electropolishing, the aluminum surface became smooth and was replaced with nodules. The formation of the nodular structure was favored at the 4.3 volts than at 6 volts. Increasing polishing times created a more defined and prominent nodular structure. Results of the AFM analysis agreed well with the results of the SEM imaging, confirming the ridge-like structures in the unpolished specimens and the occurrence of hemispherical protrusions after electropolishing. The AFM results indicated optimum electropolishing times with minimum RA per voltage setting, which are 25 minutes for 4.3 volts and 15 minutes for 6 volts. Non-uniform current distribution, likely due to the interaction of the ionic liquid molecule and the electrical double layer, may explain the nodular structure formed at the surface.
At this point, I would like to acknowledge the Sustainable Electrochemical Technologies Laboratory or SET Lab, the M Department, and of course, the Antonio and Lourdes Tanchuling Mining Engineering Centennial Professorial Chair Award.
Before I end, I would like to greet Engineer Antonio Tanchuling a wonderful birthday in heaven. I am sure the angels are throwing you the sweetest birthday celebration.
And that's the end of my presentation. Thank you very much for listening.
All right. Thank you, Dr. De La Peña, for that presentation. We may now open the floor for questions. You may type in your questions in the question box. Dr. De La Peña, here's one. In the AFM measurement, what was the scanning area? And how can you correlate your AFM image with the SEM image?
Thank you, Yoro. Before I answer the question, I just want to correct. I think I just learned that Sir Antonio Tanchuling is a medical doctor, so it should be a Dr. Antonio Tanchuling. Yes, okay. So to answer the question, well, the area that was scanned, I think it's 25 centimeters squared by 25 centimeters squared. And for the second question, what's the second question? Sorry.
Sorry. The second question is, how can you correlate your AFM image with the SEM image?
Okay, so if you recall in the slides, in the SEM image, we see nodules. So there's nodular structures. And on the other hand, when you look at the AFM analysis, the nodules represents the ridge-like structures. So as we increase the time, there is a difference in the topography, surface topography of these nodules. So it is actually related to each other by seeing that the nodules are being flattened as we increase the polishing time. So that is how we correlate those two.
All right, thank you, Doc. A related question, how many AFM image or data points did you use for the measurement of roughness, average roughness?
I think what they did was they did a line. I'm not sure about the number of data points, but they did a line AFM analysis, if that is what it's called. So hindi lang siya isang portion. So I think it's a line analysis. That's what they did.
Yeah. I mean, did you choose several sites for tapos in average yung
Yes. Yes.
Yeah. All right. Another question. Can the ethylene solution be reused for electropolishing?
The ethylene solution can be reused. So isa yun sa another study namin that is being conducted now in the laboratory, which is the reusability of the ethylene solution. So that is another part of a study wherein we are just using temperature. So ang ginagawa namin is, because ethylene solution, they are very sensitive to moisture. So nag-absorb sila ng moisture a lot. So what we did was we reheat the ethylene solution para mawala yung water doon sa system. And I think after several reruns, we've proven na nawawala yung water dun sa system just by reheating it at a certain temperature. So yes, it can be reused. It can be recycled.
Right. Any comment on the driving mechanism for nodular structure?
Okay. Well, the mechanism for the appearance of the nodules is quite new. And there are several models that has been proposed, but based on what we observe from our experiments, these nodules can be caused by the localized or non-uniform distribution of current to the system. So that is why it is being etched doon sa edges ng grains, and then naiiwan yung gitna niya. So hindi siya masyadong nai-etch. So we want to address it. So i-expand ko na yung tanong. We want to address it by surface preparation siguro. Yun yung tinitingnan naming way to be able to address that issue of nodular structures. And another way is to apply convection dun sa aming system, because right now this electropolishing is done through normal convection lang. So wala siyang any agitation. So we think that if we put in convection doon sa process, we can have a fairly distributed current doon sa system. That is causing the nodular structure, of course.
All right. I think we have time for 2 more questions. Here's one. Which companies should we convince to support further research or to host live applications as test beds?
Okay, right now I'm looking at the electropolishing shops here in the Philippines. Actually, there are 50 electropolishing shops according to the latest survey that was done by the MIRDC. And these shops are the target beneficiaries of this technology. Well, we can introduce the technology to them and hopefully they can be able to adopt it and they can be able to use the electrolyte that we want them to explore. I hope they are open for that. So mostly mga electropolishing shops.
Thank you, Doc. We have time for one more question. We still have questions. Okay, one last. Hi, Doc Eden. The 4.5 volts was used to electropolish how much area? Just curious on its upscaling.
Our experiments ngayon is in a lab scale. So to be honest, maliit pa talaga yung area. It's just 1 centimeter squared. So napakaliit pa niya. And I am currently attending a workshop on upscaling. So doon sa process na yon, maybe we can plan kung paano namin i-upscale to into bench and then into pilot scale. So I'm thinking that the upscaling would take us around 2 years, 2 to 3 years for it to materialize. So right now we are on a lab scale and the sample is 1 centimeter squared pa lang.
All right. Okay, so if you have further questions, you can type it in the question box. Maybe we can move on now to our next speaker. Thank you very much, Doc Eden.
Thank you.
All right. For our next speaker, Assistant Professor Stan Christian G. Ejera earned his bachelor's and master's degree in metallurgical engineering in the University of the Philippines, Diliman. He has been actively part of the DMMME faculty since 2013. His research work and interests are predominantly centered around physical and adaptive metallurgy, and he currently handles the Adaptive Metallurgy Laboratory and Computational Laboratory of the department. For this award, we would like to thank the People's Asia Pacific Resources Corporation of the Toledo family. We thank Mrs. Tessie Toledo and her daughters Jenny Toledo, MET-E Batch 2000, and architect Kathleen Toledo. Here is Assistant Professor Ejera with his presentation for the Domingo T. Toledo Professorial Chair Award.
A pleasant afternoon to everyone. Today I'll be presenting our study entitled The Grain Refinement of As-Cast Hadfield Steels for Jaw Crusher Plates through Pouring Temperature Control and Microalloy. This is a collaborative work between the Department of Mining, Metallurgical and Materials Engineering and the Metal Industry Research and Development Center. Before I begin, I would like to thank the donors of the Domingo T. Toledo Professorial Chair Award. To start my presentation, let me first introduce our material, which is Hadfield steels. Now, Hadfield steels are a class of manganese alloys. The name Hadfield steels actually comes from its inventor, an English metallurgist, Sir Robert Hadfield. The common composition of Hadfield steels is 12% manganese, 1.2% carbon, but there are some AMS that have a variation with their manganese and carbon content. But Sir Hadfield, through his series of experimentation, has found out that the optimum performance for manganese steels is when the carbon to manganese ratio is around 1:10. Hadfield steels is quite known in the industry because of its superior toughness, work hardening capability, excellent ductility, and high hardness. Because of these unique properties, they are suited in applications where there is high impact and high wear. Some of the examples of their applications are crusher plates, and in this study, to be exact, we are dealing with jaw crusher plates. Can also be used for grinding mill liners, cement mixers, impact hammers, and transportation, and other several transportation equipment. What gives AMS its unique properties is the presence of austenite. Austenite, also known as the gamma phase, is an allotrope of iron that is only usually stable at higher temperatures. At lower temperatures for plain carbon steel, ferrite is the equilibrium phase. Ferrite, also known as your alpha phase. Now ferrite has a lower toughness as compared to austenite because of the difference in their structures. Ferrite has a BCC structure as compared to austenite's FCC structure. Your cementite Fe3C and manganese carbide, which is Mn3C. But it is worth noting, however, that austenitic manganese steels are much more expensive than plain carbon steels because of
I think we're having some technical difficulties. We can just wait for uh, the presentation to go back for a while. Meanwhile, we would like to clarify Doc Eden got the greeting right the first time. Engineer Tanshuling, the father, is the one in heaven. Dr. Tanshuling is a medical doctor. Thank you, Doc Bebeng, for this clarification.
Yoro, if I may, I can share my own screen. I have the presentation ready. Or
I think,
is Neri? Okay, okay.
yes. Okay, while we're getting back to the presentation, we just like to mention Mr. Toledo was an ME Batch 67 graduate. ERDFE member who passed away in 2003. He set up the chair in 1996. Thank you, sir. That.
relationship. We can see from the graph and for this particular study, we aim to improve the mechanical properties through grain size refining by changing certain parameters that allows the further grain refinement of the ASCAST austenitic manganese steel. The general methodology for this study involves number one, melting and homogenization via induction furnace. Number two, ladle transfer and microalloying with 0.01, 0.03, and 0.05 weight percent titanium and 0.06 weight percent cerium. So our two microalloying elements for this study is actually titanium and cerium. Then we pour the molten metal into the molds at a pouring temperature of 1370, 1410, and 1450 degrees Celsius. After collecting the samples, we did metallographic analysis via optical microscopy. From here, we can compute for grain sizes and look at the progression. So the results of the study show that temperature has a direct relationship with grain size. And if we plot the grain size versus the pouring temperature, we can see that it has a linear relationship. We can see from the graph and the microstructures shown here that the grain size is larger when the pouring temperature is higher. And at lower temperatures, we can expect finer grain sizes. To understand how grain size is affected by temperature, we need to describe the mechanisms involved in grain structure development. Grain sizes can be directly attributed to the rate at which the metal solidifies, and this is dictated by two functions, namely the nucleation rate and the grain growth. So nucleation rate is simply the rate at which nucleation sites are made available for the formation of grains, while grain growth is the rate at which these grains increase in size before they complete the solidification process. Now, when your nucleation rate is faster than your grain growth, we have rapid solidification, and this rapid solidification results in finer grain structure or smaller grain sizes. Conversely, the opposite is true for slow solidification, which results in coarser grain structures. At lower temperatures, the driving force to produce the nucleation sites is greater because the temperature is not far off from the liquidus line or the melting temperature of the metal. Moreover, at lower temperatures, the temperature gradient is lower as compared to higher temperatures, and therefore the grain growth will also be slower, since temperature gradient is one of the driving forces for grain growth to occur. Therefore, at lower temperatures, the combination of higher nucleation rate and the grain growth and lower grain growth rate will result to finer grain sizes. Results also show that temperature not only affects the grain sizes, but it also affects segregation of constituents of the microstructure. So here we can see from left to right, this is from 1370, 1410, and 1450 degrees Celsius. We can see that there is a difference between the number of carbides, or the number of precipitates within the grains versus the number of precipitates along the grain boundaries. So we can see that the intergranular precipitates, or the precipitates that are located along the grain boundaries, are present in all three temperature ranges. However, when we proceed to higher temperatures, we can barely observe any precipitates within the grain in the lowest temperature setting, while at the highest temperature setting, we can see that there is numerous amounts of precipitates that are within the grain. So as discussed earlier, slow solidification is expected when pouring temperature is high. Through slow solidification, second phases can readily grow or diffuse into favorable equilibrium positions. And in this case, these are the vicinities within the grain. So the availability of both time and thermal energy will allow for this to occur. With rapid solidification, however, that is conditions that are favored by lower pouring temperature, there is not enough time for the fusion to occur. Therefore, it produces a more segregated structure. So during the solidification process, the solute, which is in this case carbon, and the other alloying elements, is continuously rejected into the liquid phase, which effectively enriches the liquid melt. So because of this enrichment, the liquid can reach eutectic compositions, and when it reaches eutectic compositions, this will be the last to solidify and will grow preferentially at those high energy areas. And in terms of microstructure, these high energy areas are our grain boundaries. The eutectic phase for steel is actually perlite, and if we zoom in into the intergranular intergranular precipitates, we can actually see that this has lamellar structure, which is indicative of the perlite structure, perlite being the eutectic structure of steels. So in terms of processing, these results somehow become a challenge, no? Because on one hand, decreasing temperature is favorable since it produces the finer grain structure. But on the other hand, increasing temperature also improves the performance because it produces a more homogeneous microstructure. It seems therefore that a balance must be struck between lowering the pouring temperature and increasing the pouring temperature so as to achieve an optimum setting that balances out grain refinement versus homogeneity. Now on to our first microalloying element, which is titanium. And it is seen that titanium is indeed an effective grain refiner. As we can see in this chart right here, when 0.1% titanium is added to either to the lowest pouring temperature setting or the highest temperature setting, and a decrease in grain size is always observed. So titanium's grain refining ability is very much related to the formation of titanium nitride or titanium carbide. So if we can see this as this is an SEM EDX image of our of one of our samples containing titanium, and we can see that there are regions or precipitates that contain high amounts of titanium. And so if we zoom into one of those precipitates, we can see that it actually contains a lot of carbon, titanium, and nitrogen, which says that this precipitate is most likely titanium nitride or titanium carbide or a combination of both of them. Now, the formation of these high melting point compounds, titanium nitride and titanium carbide, is the main reason why titanium is known for its grain refining. Pure titanium and its compounds solidify several hundred degrees higher than the pouring temperature of AMS, which means that during the pouring stage, titanium and its compounds will already be in its solid state. These solid titanium compounds will act as inoculants that provide nucleation sites for heterogeneous nucleation to occur. And as I've mentioned or discussed earlier, when we have increased number of nucleation sites, we increase the nucleation rate, which again increases solidification rate. And by increasing solidification rate, we effectively decrease the grain size, producing a finer grain structure. It must be noted, however, that there seemingly is an optimum concentration when it comes to the addition of titanium. So as we can see here, this is a graph showing the grain size versus the percent titanium added to the austenitic manganese steel. So this is 0% titanium. This is at 0.05% titanium, and this is at 0.3% titanium. So as we can see, When we add titanium, there is a drastic decrease in the grain size. But beyond this point, adding more titanium does not drastically change the grain size after this point. This tells us that there is a point of diminishing returns when it comes to the addition of titanium, such that adding more titanium will not give us any more improvement to the grain refining or to the grain refinement of our austenitic manganese steels. So this is the microstructures of the three samples I've shown in the graph. This is at 0% titanium. This is at 0.1% titanium, 0.05% titanium, and this is at 0.3% titanium. So we can see from the microstructures that at 0% titanium, we have very large grain sizes, but with the addition of titanium at 0.05 and 0.3%, we can see that the grains have actually become smaller or more refined. Now, the results for cerium has a sort of strange interaction with temperature. So at lower pouring temperatures, it is seen that it has a proper grain refining effect, but at higher temperature, the opposite is true. We have a grain coarsening behavior. So if you can look at this is at 1370 degrees Celsius, and there is a drop in the grain size, which means that cerium is a good grain has a grain refining effect. But at 1450 degrees Celsius, cerium does not anymore promote grain refining, and in fact, it promotes the opposite, which is grain coarsening effect. I've reviewed several papers related to cerium as a grain refining element for different systems, and the mechanism as to why cerium has a significant interaction with temperature is still relatively unknown, and I think this is a good starting point for future researchers to really look into how cerium behaves as a grain refinement with putting temperature in mind. In summary, we can make the following conclusions. Number one, when we want to cast Hadfield steels, an intermediate pouring temperature is optimal. So again, this is because at lower pouring temperatures, we can expect a finer grain structure, which is favorable for better mechanical properties. But on the other end, at higher temperatures, we can expect better a more homogeneous structure, which is also good for mechanical properties. Therefore, the intermediate pouring temperature will be a balance of grain size and homogeneity. Number two, titanium is an effective grain refiner for Hadfield steels. Its effectiveness, however, has a point of diminishing returns, and for this study, it tapers at 0.05 weight percentage. And lastly, number three, cerium's grain refining or coarsening effect has a significant interaction with pouring temperature. So when casting austenitic manganese steels with cerium as the active grain refiner, it must be cast at a low temperature for grain refinement to be observed, because at higher temperatures, cerium will actually have a great grain coarsening effect. And with that, I can end my presentation. Thank you everyone for listening. And again, I would like to thank the donors of the Domingo Toledo Professorial Chair Award. And I hope everyone had a wonderful session today.
All right. Thank you so much, Assistant Professor Ehera, for that. Any questions for Sir Stan? You can type it in the question and answer box. Okay, and we start with one. Sir, with regard to the diminishing returns that you mentioned for titanium, why do you think this is so?
Well, this is because, again, if I will reiterate, the grain refining effect of titanium is solely due to the to the titanium carbon and titanium nitride that it produces during the pouring, and this acts as inoculants. And there is a point wherein when you add more inoculants, it does not actually increase the rate of, or it does not significantly increase the rate of the nucleation rate. And so if the nucleation rate does not increase, then the solidification rate will not further increase, and therefore this will result in roughly the same final grain structure.
Thank you, sir. Any other questions? Okay. Will the microalloying process have an effect on the weldability of Hadfield steel? Sir, sorry, we can't hear you.
Hello, hello.
Yes, sir. Okay. Oh. Nawala ulit. There. Sir? No. Still no sound, sir. Okay. Again, sir, there's still no sound. Maybe we can
Hello,
answer in the
hello.
chat box. Oh, there you go.
Okay, hello. Definitely it will have an effect on the weldability of Hadfield seals, because in general, when you add microalloying elements, this can affect the effective na liquidus point and or the eutectic range, and therefore the weldability will be affected. But in this particular study, we did not look into it. So I hope that answers the question.
Okay. Thank you, sir. I think we have time for one more question. Okay, here's one. Let me read the whole thing. Salamat, Stan. Interestingly, Hadfield steels were the hotshot product in 1966 when Sir Tito worked with EEI Corp Steel Foundry. It has been a general purpose steel for heavy applications that you cited. With our dwindling foundry industry here now, which companies could be a test bed for further research or applications?
Thank you, Sir Tito. No? And I would understand that why Hatfield Steels are, as you put it, as the hotshot product in 1966, because it was invented in around 1882, which makes it a very widely used na product. No, for now, MIRDC is closely working with its industry partners, and I'm not sure because I haven't got a chance to talk with Lemuel, but he's working with several industry partners that have bought into the improvement of the mechanical properties of Hadfield steels. These are primarily mining companies. I'm not quite sure which of the mining companies, but they are all local companies in the Philippines.
Okay, thank you, sir. Okay. Just for one last question, any ideas as to why cerium has a significant interaction with the pouring temperature?
Well, the working theory is that cerium at higher temperatures reacts more faster, or reacts much faster with elements such as oxygen, producing oxides or even sulfides. And these oxides and sulfides are when they are during the homogenization stage, they could have been entrained in the dross or the slag, and therefore it was not well integrated into the melt. And again, the main reason why these grain refiners are added is to provide nucleation sites. But if they are entrained or drawn away into the dross, which floats above the liquid melt, then it cannot do its job as a grain refiner. But I cannot confirm this yet because we did not actually uh, take samples of the dross that was produced. If for future studies, we could look into the dross, try to look at the percent concentration of cerium, and if it indeed had a spike in the concentration of cerium, then maybe this working theory is correct.
All right. Okay, Sir Stan, thank you very much for that, for your time. Mary.
Thank you, Yor.
Thank you very much, Miguel, for moderating our last session. Thank you also to all our speakers for sharing your research this afternoon. I hope everyone picked up a lot. We would also like to thank the donors for their continuous support to the College of Engineering and to the department. We would also like to acknowledge Sir Tito Aliga of UP ERDFI for their unwavering support. Now, before we conclude this program, here is Dr. Leslie Joy Diaz, the committee head of the Department of Triple M Research and Extension Committee. The Research and Extension Committee aims to provide leadership in setting up the directions for research and extension activities of Triple M for faculty, staff, and students. It also aims to recommend policies, plans, and programs, as well as implement strategies for the smooth conduct of relevant collaborative research and extension by Triple M faculty, staff, and students in service of the Filipino people. So here is Dr. Leslie Joy Diaz.
Good afternoon, everyone. Thank you for joining us to the end of this colloquium. So today you have heard about research activities of our faculty members, students, and staff in the department in our effort to make our materials matter, which essentially is our DMME Research Trust circa 2016. These essentially are enabled by clean and sustainable extraction technologies to ensure that environment is protected while we provide materials to be used for energy applications, biomaterials and biomedical applications, as well as materials that will be used to help remediate and our environment, okay, which are eco-materials. In our journey to realizing these applications and technologies, various enabling technologies are employed, redesigned or innovated to ensure that we maximize the use of materials and ensure that they may meet the performance requirements. So we also would like to share with you that we are in the process of reviewing these trusts. Thus, the questions and inputs you shared with us today will be seriously considered in our upcoming research planning. In aid of our research planning, we have some activities laid out to help us obtain ideas and better references in updating our research trust. These include a survey of current research interests of our faculty members, who essentially are the ones driving our research directions, as well as an alumni webinar where we ask some of our alumni members to share us insights on current research trends. This is scheduled on November 23, 2020. If you have time, please join us during that session again. We will be doing it again via Zoom. Should you have anything to share to us that you think can be important considerations in establishing our updated research trust, please feel free to reach us at DMME Building or through our different social media platforms before November 28, 2020. Should you miss that, still feel free to approach us since this will most likely still be evolving until the end of this academic year. With that said, we look forward to more interactions with you in other events in our social media platforms. Again, we hope you enjoyed our PCA Colloquium this afternoon. We hope you had a lot of takeaways. So thank you very much. Back to you, Neri.
Thank you very much, Doc Les, for your message. So that's it. Thank you everyone for attending our colloquium today and for participating. So for those who would like to request their certificate of attendance, you may do so by answering the short survey in this through this link below. I will also send this through the chat box. Through the chat box. And for our future webinars and events, please follow our Facebook page. And that concludes our program for today. Stay safe and see you again in the next sessions that we will be organizing. Thank you.